Hey, hey, hey.
Nick, I'll give you this one. Yep, sounds good. Oh yeah, no, we're just waiting for the opening remarks to be done over there, so that people come in. You want to grab more people from there? As you can see, we're expecting a few more minutes.
It has like a theory lunch vibe.
It's a little, yeah, it's very intimate. Yeah.
It's just like people were attracted by your advisor,
That's yeah. I mean,
but he didn't even prepare for that talk.
he should point everyone over here. He's also, I guess, he was an organizer of this, and then he like decided to, oh, hello. Then down. Wow.
No,
Down.
no, no. Then this, not
Oh,
the
then this.
this.
I see.
I was talking about more about like randomized band. That was talking about lattice
full paper.
Oh, I see. Okay, okay. People. Oh, good. Good. So
All
people
right.
should be coming. All right. This is yeah, more what I was. Okay. So I guess let's wait to just 10 past.
Yeah.
Which or 7 past.
7 past.
8 past. 8 is a good number. Like round numbers, including better luck.
It's lucky, right?
Exactly. Where's your number? This is the other show. Honestly, they would be so funny. No, yeah, actually, I'm not looking at it. I'm not really into IOPs personally. All things considered, like spinning is kind of a fad.
Yeah, exactly.
It would go away.
It
Yeah.
will go how long?
How long?
Exactly. Doesn't work. Okay. Should I go on Petron? You know, yeah, maybe. I don't know where he. I'm going on Petron. Okay. All right. Oh no, Ron is here. Ron is here. That's okay. Yeah. We thought Ron had ditched us. Yeah, we thought you were going to the other talk. Okay. So I think it is. Oh, no, it's not quite 9:08, but we'll start 9:08. It's 9:08. Yeah. Good run number. Then 3 of them. All right. So welcome everyone to IOP Fest. So I'd like to welcome you on behalf of the organizers, myself, Giacomo, and Ron, who is over here. Did not go to the other talk. Just wanted to kind of like introduce the day. I hope the microphone is working okay. Yeah, okay, okay. just wanted to introduce the day. You know, we'll take like a couple of minutes of your time, and then we'll you know, yield the floor to more interesting people. So IOP Fest is a one-day workshop about IOPs. We're grateful to be co-located with ZKProof, so that, you know, if you guys can come to this. And just, yeah. So I just wanted to kind of like set the stage for IOPs. I guess hopefully if you're at IOP Fest, you probably know what an IOP is. But just in case, here is a little timeline. So the reason we're doing it this year is because it's about 10 years since the introduction of the notion of IOPs, which appeared in these two papers, interactive oracle proofs and this concept around interactive proofs of delegating computation. So it's sort of maybe ascribed to these 6 people. So it's 10 years since sort of the formal introduction of IOPs, but I claim that kind of the story goes in both directions from that. So IOPs obviously did not appear like out of nothing, right? They have their roots in this sort of ancient complexity theory of the early 90s, right? So as they were building the Colosseum, they were also thinking about sum check and, you know, IP equals P space and the classical PCP theorem. And so it has this sort of long history, sort of dating back to these breakthroughs in complexity theory and proof systems in the early 90s. There is also this important paper of Yael Kalai and Ran Raz, where they define these interactive PCPs, which are kind of maybe the closest precursor to IOPs. Since 2016, a lot of really cool stuff has happened, and we're going to hear about a lot of that today, so I won't go into a lot of detail. But you know, now we have constructions which are in some sense asymptotically optimal for these IOPs, which is very different to things like PCPs, where we still don't know. People have actually deployed these things in practice, whereas kind of to the left of 2016, all of this stuff is really like theoretical. You know, we also understand things about post-quantum security, and the post-quantum aspect of these systems is very important. Sort of looking ahead from where we are today, I mean, we've come a long way, but I want to say that this field is like nowhere near closed. So I guess we'll have Dan talking about the proximity gaps conjectures. And then I think there are, you know, many interesting directions that you know, that are open to explore, including, you know, designing proof systems from new codes, and maybe, you know, what IOPs can say about quantum complexity. This is quite an interesting thing that you know, maybe is a little bit out there. So at the end of the day, we're going to have an open problems session, and hopefully, you know, we can talk about some of these things. So that's my little spiel about IOPs and why they're so great. Just to you know, give you the schedule for the day. So we are here. I will be done in just a minute so that I can introduce Pratyush. Then we'll have a break. Then we'll have Dan talking about the proximity prize, which is like a sort of a keynote session. I think it is not in this room, but in the next room. Then we have a long break. This is because there's another keynote for ZKProof, Justin Drake's keynote, that we didn't want to overlap with. I think that will be very interesting, and, you know, shares a lot with what we're talking about in here. So please go to that. And then we have Ale talking about proximity tests, Noor talking about IOPs with linear prover complexity with small round complexity, and then in the afternoon we have Will Wang talking about interactive oracle reductions and these accumulation schemes, and then we'll finish the day with our open problem session. So please, if you have any open problems, please think of them, and we'll don't solve them until 5 p.m. today. Okay. Yeah. So please come along with your open problems that you're interested in, and maybe, you know, share them with the group. All right. So with that said, let's get started. Yes. And I would like to say a big thank you to Giacomo for doing most of the work. Yeah, yes. Yeah. Right, yes, that's true. Okay. So our first speaker will be Pratyush. If he can figure out the technology, great. So Pratyush is a professor at University of Pennsylvania. He's done a lot of great work on IOPs and other kinds of proof systems over the years. And he's going to tell us about the quest for optimal IOPs. So,
Okay. Hi, everyone. Good morning. Thank you, Nick, for the great introduction, and thank you, Nick, Giacomo, and Ron for organizing the wonderful workshop. Okay, awesome. Yeah, let's get started. All right, so the title of my talk is a little grand, but essentially, I guess, what I'm going to talk about is how we could construct IOPs which achieve kind of maybe the best possible efficiency along certain important metrics. Okay? All right. Okay, so why are we here? We're all here because of SNARKs. I think I don't need to explain SNARKs to this audience, but I'll do it anyways because every talk needs a SNARK intro. Okay, so basically SNARK is this protocol between a prover and a verifier, where the prover makes some claim that some function is, makes some kind of NP claim that asserts that some function is satisfied by some public input X and some private witness W. Okay, and it's able to do this by sending a very short proof that can be checked quickly. Okay. And the properties of SNARKs have led to lots of deployments, such as improving the scalability of these decentralized ledgers, in the future maybe in private digital ID systems as well as private cryptocurrencies, right? And the reason why they've seen all of these deployments is because they have some very nice properties. And what are these properties, right? What are the properties that make them applicable to these applications? Well, there's a few that we care about. The first is, what kind of assumptions that we can build these SNARKs on. So something like, elliptic curve-based assumptions in the ROM, so on and so forth. Okay. How fast is the prover? How long does it take to actually produce this proof? How fast is the verifier? How long does it take to check this proof? And what is the proof size, right? How large is that object from the prover to the verifier? Okay. All right. So kind of the state of the art, or the standard that is developing or emerging today, is that for all the applications that people care about, people are using SNARKs built on IOPs. Okay, I'll talk about what IOPs are in a second. But actually the reason for this is because these SNARKs built from IOPs, they kind of fare well in all of these metrics, or fairly well in all of these metrics. On the soundness, on the assumption front, they have transparent setup. They can be constructed in the ROM. And they're plausibly post-quantum, right? So they have a lot of nice things going for them. On the prover efficiency front, they're fairly fast after, I guess 10 years of effort. We've been able to construct these SNARKs, which have very good prover time. They also have kind of state-of-the-art verifier time with things like WIR, which are faster than even maybe the best SNARKs from other assumptions. Maybe the only place that kind of falls short is that they have large proof size compared to other SNARKs, right? So orders of magnitude larger than, say, curve-based SNARKs. Okay. So in this talk, we'll see how to maybe address these shortcomings, improving the proof size while preserving or improving the other metrics. Okay. All right. So to see, why SNARKs that are constructed from IOPs have this kind of property, or have these properties, let's take a look at IOPs, right? So an IOP is basically this, we're all here because we love IOPs, but again, I have to introduce what they are. So an IOP is this interactive protocol between a prover and a verifier. The prover sends a message, the verifier responds, and this continues for some number of rounds. But unlike a standard interactive proof, the verifier doesn't have to read all of the messages, right? At the end, it can decide to query some of these messages, just read some individual symbols, and make its decision on whether to accept or reject based on that. Okay? And IOPs can be constructed or can be compiled into SNARKs with this kind of two-step process. In the first step, what we do is instead of sending the oracles, we just commit to them using some vector commitment. And then whenever the verifier wants to make some queries, it just tells, hey, prover, what are the elements at these query locations? And the prover responds with these elements as well as the opening proof. Okay, and this gives you an interactive argument. And then this can be compiled down into a non-interactive argument via Fiat-Shamir. Okay. Okay, so this is the high-level construction. I'm blazing through it because it really doesn't matter. What we really care about is how the efficiency of the IOP kind of affects the efficiency of the final SNARK. Okay. And here on the prover time front, kind of the efficiency of the final SNOC depends on the prover time of our IOP, as well as the time to commit to all of these oracles. Okay. The verify time is basically is basically the time to run the IP verify plus check these opening proofs, which scales, when we instantiate the vector commitment in Merkle trees, is basically q log n hashes, where q is the query complexity. And finally, the proof size is basically the query complexity times a Merkle path length, roughly. Okay. So really, the high-level picture from this is that when you want to design efficient SNOCs and efficient SNOCs from IOPs, we want IOPs which minimize the prover time and the query complexity, because that kind of optimizes all three metrics. Okay, any questions? Good, okay. All right, so let's take a look at how we design such efficient IOPs. The key tool that is used in almost all such constructions is this thing called an error correcting code. Okay, so an error correcting code is some way to take your message and encode it into some kind of redundant encoding. So you take messages in f to the k and you encode them into some string in f to the n, where f is your field, right? And we're kind of concerned with three main properties of these error correcting codes. So the first is distance. How far are these elements in the redundant representation from each other? What is the rate? How redundant is the representation? Okay, and how long does it take to encode? Okay. Additionally, just a couple of notes. In this talk, we'll only be looking at linear codes, so codes where the code words form a subspace of f to the n, and where the encoding process is a linear map. Okay, and also generally, we'll just focus on cases where delta and rho, the distance and the rate, are both constant. Okay, all right. So these are error correcting codes. How do we construct IOPs from error correcting codes? Well, it's basically, kind of a two-step process. So in the first step, what the prover does is it takes its witness and encodes it using the error correcting code and sends this oracle. And then the prover and verifier engage in some kind of protocol which reduces this NP claim, the satisfaction of this function, to some claim about the proximity of the oracle sent in this interaction to the code. Okay. So that's at a high level. You also have sometimes some other simple claims about the messages underlying these codes, but we'll kind of brush that under the rug for this talk. I think Ali's talk will cover in more detail, how to handle those additional claims. Okay, so after we've reduced our NP claim to this proximity claim, almost all IOPs, what we do is that we kind of just prove this proximity claim. Okay, so we invoke an interactive protocol that asserts that the oracles that were sent in the first step are close to the code. Okay. So the step is also called an interactive oracle proof of proximity. And as it turns out, basically the efficiency of all the efficiency metrics that we care about for our IOPs kind of stem from the choice of code and the IOPP that we can develop for it. Okay. This is because kind of the first step we have nearly optimal constructions, where essentially, for example, in the Spartan based IOP, you only have to encode the witness and nothing else. Okay, kind of all of the efficiency of our IOP just comes from the encoding time of our code plus the encoding time or the running time of the IOP prover or IOPP prover, and the query complexity kind of almost entirely stems from the query complexity of the IOPP. Okay. So really what we want to focus on and what this talk will talk about is optimizing this last step, how to design efficient IOPPs. Okay, any questions? So feel free to stop me at any point and ask questions. Okay, all right. Yeah, so just to summarize, what we want is we want a code which has fast encoding time to minimize that T sub C, and we want an IOPP for C which has fast prover time and low query complexity. Okay, all right, so this observation that we want fast IPPs is not a new one, right? Kind of this goes back to the very beginning of the world of IOPs, and people have been at this effort of designing efficient IOPPs for the last almost 9 years, right? Okay, so the first work in the space was kind of Ligero, and what it did was it designed an efficient IOPP for Reed-Solomon codes. Okay, or Interleaved Reed-Solomon codes, and achieve this kind of query complexity of roughly square root and a encoding time of the code of n log n, because we're using Reed-Solomon codes. Okay, so this is kind of the initial work in the space, like 9 years ago. Okay, and at that point, kind of the research community bifurcated its efforts into two directions. Okay, the first direction tried to improve the query complexity while leaving the encoding time alone, and the second effort tried to start improving the prover time or the encoding time. Okay, so on the first branch, we had a beautiful sequence of works, fry, basefold, stir, whir, which eventually culminated in this lovely work from Minzer and Zheng last year, which reduced the query complexity down to kind of what's optimal. Okay, just lambda queries to achieve a soundness error of 2 to the minus lambda. Okay, it didn't really, again, optimize the encoding time at all, so encoding time is still quasi-linear, just n log n. Okay, on the other branch, people were also, doing work, and here they try to improve the encoding time by moving to a new class of error-correcting codes, specifically linear time encodable codes. Okay, so things like the breakdown code or the Spielman code. All right, and while the initial works, again, they kind of just had the same query complexity as Ligero, eventually, via a sequence of works, we were able to improve this down to, almost close to what we had on the other branch, so namely lambda log n, but still, not quite where we want to be, which is optimal prover time and optimal query complexity. Okay, so it's kind of the state of the art until roughly middle of last year, and then kind of maybe late last year, there were a couple of works which kind of allowed us to join this fork back down and obtain IOPPs which achieved the best possible encoding time, which is O of n, and also this best possible query complexity of O of lambda. Okay. So in this talk, I'll basically cover at a high level kind of each of the milestones along this journey, starting from Ligero and then eventually moving through this lambda log n query complexity IOP, lambda log n, and finally culminating in the optimal query complexity IOP. Okay. Yeah.
Is this always bit complexity?
This is everything is just assuming fields. So the query complexity is in terms of symbols is field elements. Sorry. Oh yeah, this is kind of talking about maybe I would say efficient constructions or concretely efficient constructions. There's an entire literature before this of PCP-based construction, or PCP-style constructions, which achieves, a different.
No, I'm saying where. Am I wrong about this?
Were? Oh.
I mean, I always understood that were is O of lambda, because it's like lambda plus lambda over 2 plus lambda over 4. Because
Those are all field elements, though.
Oh, that's what I was asking.
Yes.
Is it bit?
This is field. Everything is in terms of field elements.
Right. So that's what I'm saying. So I always understood that in were you can get O of lambda. Am I wrong, Giacomo, about that?
I think. Yes. Yeah, so you can grow the alphabet size in were and stir, and maybe not, I don't know for stir, but at least for were, and then you can achieve O of lambda query complexity there, but then it's not for constant alphabet.
Oh, okay, so it's not O of lambda field elements.
Yes, it's O of lambda log n field elements for were. Yeah.
Thanks.
Okay, all right, thanks for the question, Ariel. Okay, any more questions before we start diving into kind of the technical portion of the talk? No? Okay, all right.
If you have a question, raise the hand and the mic will get to you.
It's a magical mic. Okay. All right. So let's take a look at this first step. How do we achieve even this IOPP with square root query complexity? Okay. To do this, we'll kind of start off with a very simple IOPP that basically reduces multiple proximity claims to some code C to a single proximity claim. Okay, and we'll formalize this with this notion of an interleaved code, which you'll hear about quite a bit over the course of the day. Okay, but basically, if we have some base code C with block length R and message space S, you can construct a t-wise interleaving of that code by basically taking your message, which is an s to the t, arranging it as this matrix, and then encoding each row of the matrix using your base code C. And this will give you kind of the interleaved code word, where each row in the code word is a code word in the base code C. Okay. So this interleaved codes there, it's a very, very simple construction. You just encode each row. They have some nice properties. So the rate is the same as the rate of the base code. The encoding time is essentially proportional to the, what you would expect is proportional to the encoding time of, again, the base code. But the distance is kind of worse. Okay, it degrades with the interleaving factor. At least if you consider it over F. If you consider alphabet to be kind of one column, then it has the same distance. Okay, and this is kind of where were, for example, would achieve, by doing this, were would achieve the O of lambda query complexity. But over F, it has poor distance. Okay, all right. So how are we going to construct an IOPP for these codes? Well, okay, so the claim is going to be that the prover is telling the verifier that there exists some message M such that this oracle, which is claimed to be a code word, is actually close to that encoding of M under this interleaved code. Okay, so that's the claim that the prover is trying to prove here. That's the proximity claim. Okay, and the protocol is very simple. All right, the verifier just samples a random challenge and sends this over to the prover. And the idea is that this challenge gamma is going to serve as basically a random linear combination challenge. So the prover is going to use gamma to combine all of the rows with respect to the coefficients, which are just powers of gamma, right? And it's going to send over this code word C star, which is supposed to be in the base code, and it's supposed to be a linear combination of these CIs with respect to the powers of gamma. Okay? All right. So in some sense already, assuming things work out, we've kind of reduced our work, right? Earlier we had this T size or T times K sized claim, and now we have just a K sized claim. Okay? All right. So to actually make this protocol go through, the verifier does a few things. Okay? So the first thing it does is it basically samples some, random columns in the interleaved code, and checks that the linear combination of the elements in these columns equals the corresponding location in C star. Okay, so in this new code word that the prover sent. Okay, so it does this enough times so that it gets some guarantee that, okay, actually these two are indeed linked. So C star is indeed the linear combination of these CIs. Okay, and then what it does is the prover also sends along some message M star, which is purported to be the message underlying C star, and the verifier just checks that this is the case, that C star is indeed an encoding of M star. Okay? All right. So at a high level, you just take linear combinations along random columns and check that they're consistent with the new code word, and then you check that the code word is a valid code word. Okay, that's a high level construction. Okay. So let's analyze the properties of this. So completeness kind of follows straightforwardly, but we can still quickly go over it. Since the prover is honest, the code that it will send will actually be the linear combination, so the spot checks will all pass. Okay, and now essentially since the code is linear, right, the prover can actually construct this M star and send it along, and if you work out the math, you'll see that this re-encoding check will also pass. Okay, so both of the checks of the verifier will pass as long as the prover is honest and the claim is true. Okay, all right. So soundness is a little bit more tricky, but still not too complicated. So in the soundness, the case is that we have that the verifier accepts, but the claim is not true. Okay, so there is at least one row which is far from our base code C. Okay, and then we can divide the soundness analysis into two cases, or maybe we'll see three cases really. So the first case is that the sent code word is far from the base code C. Okay. In that case, the verifier will just reject because it'll try to encode M star, and then it'll get some code word which will be far from C star, and so the re-encoding check will fail. All right. So moving forward, we can kind of assume that this re-encoding check passes, which means that C star is actually close to a code word C. Okay. Now we have two cases, right? So if C star is close to C, it might be the case that C star is actually a linear combination of all of the rows. And in that case, it's going to be true via proximity gaps that, this is a linear combination of these, but one of these is far from the actual code, that's going to happen with negligible probability. Okay, so proximity gaps ensures that this linear combination claim only holds or implies that all of these codes or claimed code words are actually close to the code. Okay, all right. So that's a case. Now we're left with the other case, which is basically that C star is close, but it's not close to a linear combination. And in this case, if you do some math, you can see that if you make like lambda many spot checks, these lambda many columns, at least one spot check will fail with all but negligible probability. Okay. And maybe, I don't know, you don't want to remember this expression, but we'll come back to this expression of this lambda over log 1 minus delta C. It'll reappear later. Okay, anyway, so the high-level takeaway is that this is the essentially full proof of this protocol. There's some details that you can work out, but this is the intuition. Okay, all right. What about efficiency? Okay, does anybody want to help me with what the efficiency, the query complexity of this IOPP is going to be? I've been designing a lot of slides for classes, so I'm in a pedagogical mood. Okay, we started off with one goal. What's going to be have we achieved that goal? How many symbols do I read in the spot checks? Okay, and we're all making. Okay, it's going to be T. We're all waking up. Maybe we need to get some coffee. Okay, so all right. So the prover time is basically going to be encoding time plus the time to do the linear combination. But the number of queries is going to be the number of spot checks times the interleaving factor, because we have to read all of these columns, plus the time to read this message, okay, and also read this code word. Okay. So now when we're encoding k-length messages, what we want is that this S times T is equal to K, right? And if you plug that constraint in, you basically get that the query complexity, this expression nu times T plus S, where nu is the number of spot checks we make, is minimized roughly when you set T and S this way, so roughly square root, okay? And this basically gives us a query complexity of K times lambda. Okay, so in this talk, generally, as I said, we're going to be using constant distance, constant rate codes. So I'll interchangeably write K and N because they're just off by a constant factor. Okay? Any questions? No? Okay, all right. Either I've been exceedingly clear or I've already lost everybody in the audience. Okay, all right, so this is our modest goal that we set for ourselves, that we get this square root query complexity. Let's see how we can do better. Okay, so what we're going to do is we're going to reduce the number of queries by, in some sense, interleaving less. And our goal will be to achieve, in this chapter, is going to be achieve an IOPP, which gets us like a logarithmic query complexity. Okay. All right, so let's take a look at why this previous IOPP is expensive. To do that, we can see that we can actually split up the IOPP into two steps. Okay. What happened to this? Okay. So the first step is this interactive reduction, which takes our claim about proximity to the interleave code down to a claim about proximity to the base code. Okay, and this requires this lambda times T number of queries. Okay. Second step is this naive IOPP for this base code C, which is basically just re-encode and check that you actually have a code word. Okay, and this has O of S queries. Okay, and we can take this picture and abstract it a little bit, by talking about the first step is this reduction from K to K over T sized claims, and an IOPP to assert this K over T sized proximity claim. Okay. All right, so far in this previous protocol from the previous chapter, right, we took this, abstract protocol and instantiated it in a way that balanced out the query complexity in step 1 and step 2. Right, this got us our square root query complexity. Okay, so the natural question to ask is, what if we didn't balance, right? What if we wanted to minimize the query complexity in one of the sides, let's say in the reduction? Okay. So we kind of now go to the extreme. Instead of setting t to be the square root value, instead of interleaving square root times, we're just going to interleave twice. Okay, so we're going to go from some 2 y's interleaving of c down to just 1 code word of c. Okay, so we've halved our proximity size claim. Okay, what query complexity does that give us in this first reduction step now? Yeah, it's lambda. It's like 2 times lambda, right? Because you can see the number of queries in the first step is lambda times t. T is equal to 2, so 2 times lambda. Okay, so nice. So we've really improved the query complexity in this step. We've got it down all the way down to lambda, okay? But then what happens to the query complexity in this step? It goes up, right? It goes up all the way to k over 2, right? So we've kind of actually gotten worse. The sum of the 2 query complexities is worse than what we had before. All right, so this is not great, right? But, okay, now I claim there's something that we can do, right? And this is kind of, what we can do is invoke the oldest trick in the computer science textbook. What is that oldest trick? Recursive, right? Instead of actually just proving this claim immediately, this proximity claim for ck over 2, we're instead going to imagine that we have another reduction, which can maybe take us from ck over 2 down to ck over 4. Okay. Oh, by the way, I've just abstracted out the codes. So ck in this case, in the protocol that we have so far, is this interleaving or interleaved code, and ck over 2 was the base code. And you can imagine ck over 2 is another code which has maybe another interleaved code of overall message length k over 2, and ck over 4 is that code's base code, and so on and so forth. Okay. All right. So now, if we had these reductions, which allow us to iteratively have the claim size every time, we can basically recurse log k times and eventually get out some constant size claim, and then we can just check that via our naive IOPP. Okay, so everything will work out. Okay, so we have now, I guess, a few questions. First, can we actually construct these reductions? Second, is this actually sound or complete? And third, what is the efficiency of this? Okay, so let's answer each of these questions one by one. All right, so what we're going to do is, okay, there's some animation mismatch, but we're going to set, imagine that we have some base codes B, okay, which have these message lengths, k over 2, k over 4, k over 1. They can be fairly arbitrary, with one restriction that I'll come to just in just a second, okay? Then we're going to set each of these CIs, the CK over 2, and so on and so forth, to be the interleavings of these base codes B, okay? All right, this allows us to construct the reduction as follows, okay? So we're going to have first this kind of folding protocol, which is basically taking the linear combination of the rows of the interleaved code. And this allows us to go from a claim about proximity in the CI code down to a proximity claim in the in the BI over 2 code. Okay, so this halves the claim size. Okay, so this step reduces the size of our claim. All right, but now we're kind of stuck, right? If you want to invoke this again, we need as input to it some kind of interleave code, right? But now we said that B can be just an arbitrary code, not necessarily an interleave code. So how are we going to keep going? Okay, how can we invoke this reduction again? And here is where we will mention then and not talk about this beautiful idea called code switching, which basically allows us to take our proximity claim about these base codes B and reduce them to proximity claims about essentially arbitrary codes. And in particular, in this case, proximity of arbitrary or to arbitrary interleave codes. Okay, it's kind of the next smaller size interleave code. Okay, so put together these two steps, what they do is that they take some claim about interleave code of size, let's say k. They switch to an interleave to a proximity claim about the base code of half the size, and then they reduce that proximity claim down to a smaller proximity claim about the next interleave code, which is of half the size again. Okay, so we started with a claim about, let's say, ck, then we end up with a claim about ck over 2. Okay, all right. So again, I won't talk about code switching too much, but I'll just mention that we have over the past, I guess, 5 years. Many beautiful works which construct code switching for a vast variety of codes. So RAA codes, LDPC codes, breakdowns codes, tensor codes, so many codes, and even things like kind of Reed-Saltman, you can think that they have like a natural succinct code switch in them. Okay, so essentially we have very efficient protocols for this code switching step for many codes that we care about. So really what we'll care about in the rest of this talk is basically this first step, the folding step. Okay, any questions? Okay. Yeah.
When you mentioned the breakdowns code, it's like a linear encodable code, so this code switch also works for.
Yes. Yes. Oh, yeah, just to just repeat the code. I can repeat the question
Please
for
raise your
the.
hand when you have a question.
I can repeat the question for the stream or the recording is basically, does these code switches exist also for things like the breakdown code? And the answer is yes. That's via this NST25 work, which shows that they exist for LDPC codes, and the breakdown code is an LDPC code. Okay, and also I want to mention that the reductions here, they're called, I guess, IORs, which William will talk about, but you can kind of think of them as an interactive analog of NP reductions. But the high-level idea is that the prover time and query complexity is already what we want for these code switches, so we don't have to talk too much about them. We just have to focus on this folding step. Okay, all right. So IOP completeness and soundness, assuming that those folding and code switching steps are secure, which we talked about the security of the folding step, and I'm going to just assert that all those authors of those papers are probably not mistaken. Code switching is also secure. There are these composition theorems that people have developed for these interactive oracle reductions, which allow us to basically say that if the components of our reduction are secure, then the composed reduction is also secure. That also applies when we're composing these logarithmically many reductions in sequence. Okay. So overall, at a high level, just these composition theorems just tell us that recursing log n times or log k times gives us an overall complete and sound protocol. Okay. There's some details you need to take care of, but it just essentially just works. Okay. Okay. What about efficiency? Let's take a look. All right. Again, we're going to focus on prover time and query complexity. So essentially, I guess the prover time and query complexity are going to be the sum of the times in each of these steps, right? We're not doing anything special here. On the prover time front, like in each step, remember what we have to do is we have to fold the code, and we re-encode under the new smaller code. So the time is basically linear in K, or is the time to encode in K plus some additional work to do like the linear combinations and so on, and also to do the code switch, okay? But kind of the dominant cost is this re-encoding cost. And if you add it all up, kind of this cost halves at each step, because we're getting smaller and smaller claims as we go down. This means that we obtain kind of a running time here, which scales with the size of the largest code, the running time, which is the first step. Okay? All right. This is the more complicated calculation. What about query complexity? What is the query complexity of the overall protocol? Yeah, it's just log k times the number of, I guess it's like the sum of the query complexities in each step, but this is just lambda in this one, lambda in this one, lambda in this one, and so on and so forth until the end. So you get a query complexity of lambda log k. Okay? All right. So this already so this achieves our goal, but this, I set out for this chapter. Okay, so getting this nice prover time while going from square root to logarithmic query complexity. Okay, but remember our goal is to get lambda query complexity. So let's see how we can do that by first taking a baby step. Okay, we won't go all the way directly to lambda. We'll first go to log k. Yeah.
Yeah, but right, you have a code switching sort of proof at every step, which I think they do with some sum check.
Yes, so I said before that we're now going to talk about this additional claims that we have to prove about the messages underlying the code words. But you can essentially, fold those sum check claims along as well. So you can reduce those claims. You can sometimes add them to the thing that you reduce it to.
Oh, I see. So you can somehow aggregate them so you stay with the lambda log k in
Yeah,
total.
yeah, it kind of
Okay.
works out. Yeah. So and I won't talk about it. I think Ali's talk will go into more detail on how you can do that. Okay, how are we doing on time? Okay, I'm running definitely very short on time, so I'll try to speed things along a little bit. Okay. All right. So yeah, our intermediate goal is going to reduce this from log k to log k. Okay. For all practical purposes, log k is essentially just 1, right? It's like 5, but it's still, eventually a good idea to get down to even remove that 5 factor. Of course, that'll only be in theory. We'll see that the protocols which have this query complexity are much more efficient than the protocols, concretely, than the protocols which have of lambda query complexity. And maybe that'll be one of the open questions for the session tonight or in the evening. Okay. All right, so let's see how we can improve upon this protocol from before, right? What we can hope for is that if we want to achieve lambda query complexity, we can say, okay, I'm going to, say half the number of queries in each reduction. Okay, so the first reduction takes lambda queries, the second reduction takes half that, the next half of that, and so on and so forth until I get O of 1 queries in the final step. And then if I sum all of these up, I will just get like something like 2 lambda or whatever. Right? But unfortunately, this doesn't work, right? If you try to do this and you work out the calculation, it ends up being the case that in the ith round, you need distance, which scales like 1 minus 2 to the, I guess, minus 2 to the I. Right? So it kind of grows exponentially, right? And because rate and distance they have this trade-off, once you start hitting this huge distance requirement, this means that your rate must be tiny, which means that your encoding time really blows up, which means that our prover time will go up. Okay? So kind of doing this naively in this way doesn't work, right? You can't hope to reduce the number of queries in half at each step. Okay? But we can kind of salvage this a little bit by flipping things around. Okay? Instead of setting what our target query complexity in each step is going to be, we can instead say, okay, we're going to set our distance in such a way that it kind of maybe increases across rounds, and then see what kind of query complexity we can get from that. Okay. So what we're going to do is we're going to say, okay, in the first step, we're going to have some distance. In the next step, the codes, we're going to aim to have double the, I guess, half the distance. Okay. So they're going to be more redundant. Okay. And in the next one, we're going to aim for proximity claims where the distance is even half of that, and so on and so forth. Okay, so you keep doing this over the rounds. Okay, and basically this gives you the expression that in the ith round, your query complexity is this value. Okay, I don't expect you to verify this, but it's not too. You just plug this into that expression that we had from a couple of slides ago in chapter 1. And it turns out that if you take this sum now, if you sum over the number of rounds, this will kind of give you the query complexity that we aimed for, just lambda log k. Okay? All right. But there's still a problem. Okay, we're not quite done. And the issue is that in each step, we are halving the message length, but also halving the distance, which is effectively, I guess, doubling the rate at least, right? And what this means is the code word length doesn't change in each step. So in each of these reductions, we will have the same code word length or block length of, let's say, n. Okay? And then now this kind of blows up our prover time. So we go from, the encoding time halving now just stays the same across rounds. This means that at the end, we will have this additional log factor to account for in the prover time. Okay, and we want to get rid of that. We don't want that blow up. Okay, and the idea in works like stir and whir is basically what we're going to say is that we're going to fold more. Okay, so we're going to, yes, the distance is going to blow up our code words, but we're going to fold more to account for that. So instead of folding in half, we're going to fold, let's say, in fourths, okay, or in sixteenths, or so on and so forth. So we're going to shrink the code word size more by folding than the distance amplification blows up the code word size. Okay. All right. All right. So if you plug in the parameters and calculate it out, you kind of get what you want. So we end up with our prover time being just dominated by the encoding time plus and the query complexity is still the same. Okay, maybe slightly worse because now you have to account for this larger interleaving factor, but asymptotically the same. Okay, any questions? I think there's a question up here.
If you fold more, will that make the distance like also change more?
No, so we're just setting the base code to be the higher distance base code, but we're setting the interleaving parameter to be, let's say, 4 instead of 2. Okay.
Okay, but
Okay.
I'm missing a little bit.
Okay, all right. I think I have 6 minutes. I don't know how I'll get through the final, I guess, opus of this talk. Okay, all right. Okay, all right. So this kind of gets us almost to our goal. We have good encoding time and hence good prover time, and also this lambda log k query complexity. But now we can aim to chop off even this log factor. Okay, and we're going to do that by moving away from interleaving somewhat and going towards tensoring. Okay, so we'll talk about what all of this means. Okay, all right. So our problem so far in reducing the query complexity is that we have too many reductions, right? And we saw from the previous chapter that we can't reduce the number of queries in each reduction fast enough, right? If you try to have it, then your distance blows up. Okay, so what we're going to do instead is we're going to reduce the number of reductions. Okay, so we're going to reduce the reductions. All right. So what we want, basically our goal will be a constant number of reductions, each of which takes lambda many queries in such a way that at the end you have this constant size claim that you can just check. Okay. As it turns out, the goal is a little bit easier than this. In some sense, it suffices to reduce the message length just to, let's say, cube root, because at that point you can invoke, you can code switch to claim proximity claims about Reed-Solomon codes with a very bad rate and hence very good distance, and then you can invoke protocols like stir and whir, which in this regime have the query complexity we care about, just lambda. Okay, and also Reed-Solomon codes in this regime, they can be encoded in less than k time, so we're fine. It doesn't impact the overall time. Okay. So yeah, our goal is basically this kind of reduction, which takes a k-sized claim and gives us maybe the k to the 2 to the 3. I forgot it's 2 or 1 there, but it gives us a smaller claim. Okay. All right. So again, let's take a look at our reduction protocol. What we're going to do is we're going to again bump up our interleaving factor. Okay, so instead of interleaving by 2 or 4, we're going to interleave with this much higher interleaving factor of k to the 1/3. Okay, we'll see why 1/3 just kind of works out, but basically the point is that it's not constant; it's super constant. Okay. All right. We can write this just for conciseness as basically kind of an inner product claim between the columns that we queried and the linear combination vector. Okay. But again, if you had to use this as a starting point, we're kind of screwed, right? Because the query complexity is interleaving factor times lambda. So this already blows way past our budget. It's worse than the previous 2 chapters. So we end up in this much higher query complexity. Okay. Well, okay, so how can we overcome this? Well, what we can say is, hey, we have this prover at our disposal. The verifier says, hey, prover, can you help me in checking these spot check claims, these inner products? Okay? So what we want, in some sense, is some kind of IOP, which allows the prover to convince the verifier that these spot checks hold. Okay? But, okay, unfortunately, by itself, it doesn't quite help, right? And this is because to be able to be convinced of some claim, the verifier needs to know what that claim is. It needs to know what these inner product claims are. So it still has to read these columns as explicit input, right? So we've not reduced anything there. Okay. So to fix this, we could try to give the verifier oracle access to the columns instead. So just say, hey, verifier, you don't need to read the oracles in their entirety. You can just query them at random points. But this doesn't quite work, right? And that's because let's say the prover gives oracle access to the columns, which are correct in everything except one location, right? Then the verifier will never notice, in some sense, right? There's not enough distance. And then the inner product would be completely different, which would maybe allow the spot checks to pass, but the verifier would never notice. And this is the problem here is basically that a malicious column is not too far from an honest, the correct column. Okay. So okay, how are we going to fix this? Yes, error correcting codes, right? Like it's the second tool in IOPs after recursion. Okay. So what we're going to do is instead of providing these oracles in the plane, we're going to send them in encoded form. Okay. And effectively, what this means is that we're going to take our interleaved code and encode each of the columns as well. Okay. This is what's called the tensor code. That's all the tensor code is basically. You interleave and then you encode along the columns as well. Okay. We're going to, let's call these, I guess, the full columns mu sub j. Then essentially what we want now is a slightly more complicated IOP, which proves not only the inner product claims, but also this claim that these oracles that the prover sent are actually close to the encodings of whatever message is supposed to be. Okay. Okay, this is the most technical part, so ask questions, but not too many because I don't have that much time. Okay. All right.
So basically, we need usually we use marker commitment, right? Marker tree commitment. So how to commit the encoded
You can just
tensor
lay it out as a
You
a
pre-encode
lattice
them
and
and
you Merkle tree. Yeah.
okay.
Yeah. The prover it just sends now this tensor code instead of sending the interleave code. Okay. All right. Okay. So what is the simplest IOP? Well, the simplest IOP basically just well, it invokes some IOPP to check the proximity, and it just checks each of these inner product claims individually, right? But if you do this, you kind of are still worse than the previous two chapters, because you end up with some lambda squared query complexity. Okay, like each claim, there's lambda many claims, and each of those claims will require, like, say, lambda queries to each column, and this will be lambda squared. So it's too much for us. So what we need to do is design kind of a more sophisticated IOP for this claim. So let's focus on this most sophisticated IOP. And what we're going to do is we're going to have the prover send under some other error correcting code an encoding of all of these, I guess, these base messages, these SIs. Okay. So you can think of these SIs, just to remind ourselves, they're basically the columns in the interleaved code. And the UIs are the encodings of those under the column code. Okay. So the prover sends an encoding of the concatenation of all of these SIs, and then it needs to convince the verifier that two things are true. First, that this code word U is actually an encoding of the concatenation. And second, that the inner product claims hold, okay, for each of these. This should be, sorry, SIs, not UIs here. Okay. So the first claim, this close to an actual encoding of the SIs, can be broken down into two further claims. The first is that U is actually close to this code D that we chose to encode it with, okay? And that the message inside the U is consistent with UJs. Okay? So again, this is the most technical step, so stop me if there's any questions. All right? Okay. So it turns out that this claims or 1.1, 2 can be all dispatched by encoding or choosing as our code D, the Reed-Solomon code with high enough distance. Okay, so k to the half or k to the let's say with rate k to the 1/3. Okay, and this is fine because encoding is, so basically we can choose this as our error correcting code. This is fine. Encoding this is still going to be sublinear, is going to be less than k, let's say k to the 2/3. And then in this regime with this inverse polynomial distance, work and prove proximity and some check claims in one go with just O of lambda queries. Okay, so we can basically discharge all of these obligations by using Reed-Solomon codes for that step. Okay, so all we're left to do is to prove this step, that the message inside this code word U is consistent somehow with the messages in these columns, or with these columns, in fact. Okay. All right. Okay. So this is going to take, we can try 2 attempts. The first attempt is a naive attempt. Okay, so what we're going to do is we're going to go back to our favorite trick, which is spot checks. So the verifier is going to sample some random, per column is going to sample some random locations and check that U is consistent for that column at those random locations, okay? So this involves basically some claim which between the rows of the generator matrix, the ith of the generator matrix, with the jth message. Okay, I won't go into too much detail here, but the point is that if you try to do this, you end up still with quadratically many queries. Okay, this per column you have lambda queries, as lambda columns you end up with lambda squared. I also won't talk about how we prove this in a product claim. You can kind of batch it with other subject claims. Okay. So what we actually do is a little bit more complicated, and this is where maybe most of the math in this protocol comes in. At a high level, what we're going to do is we're going to sample actually more than lambda columns. Let's say we're going to sample 4 lambda columns. And then we'll kind of subsample some checks from these. Okay, I don't think I have too much time, but I'll try to go into it quickly. So what the verifier does is she samples many, many columns for lambda. And out of these, each of these, for per column, she picks a constant number of locations to query and ask the prover to prove that, okay, those constant locations, let's say here and here, are consistent with the encoded or the underlying message, okay, by multiplying with the generator matrix row. Okay, so you can kind of think of this process of multiplying with the generator matrix row as a kind of a batch code switch. Okay, so this kind of works. The query complexity is just 4 lambda. There's 4 lambda columns. Per column, we're making constant number of queries. We get this overall nice query complexity. Okay, but this is actually sound, right? This seems like a kind of unnatural thing to do compared to everything else that we've done so far. I guess I don't have too much time to go into it, but at a high level, the idea is that if our distance of the column code is half, then out of these 4 lambda or 4 new many columns, right, the number of bad columns which are far from the code is going to be tightly concentrated around the average number of bad columns, which is, let's say, 2 new. And this follows from some kind of churn-off bound, right? And this, as a corollary, you can basically know that at least lambda of these columns is bad, okay? Now, if I sample a constant number of queries per column, right, and each bad column is at least half distance away from the code, then the prover can get caught cheating in each bad column with, let's say, some constant probability. Okay, some constant probability per query, and there's constant many queries. Okay. Now, combined with this corollary, this basically, now we have a lambda number of checks, each of which fail with constant probability. The probability that none of these checks fail, which means the prover avoids detection, is going to be negligible. Okay. And yeah, if you set this new appropriately, this whole thing becomes negligible. Okay. So it's kind of like the high-level idea behind both of the works which achieve this optimal query complexity. But yeah, the takeaway is basically that if you do this, the prover time for this step is as we expect. Okay, it's just the encoding time plus lambda. Okay, I'm getting dirty looks from Giacomo next. I'll quickly wrap up. So basically, I guess in this talk, to summarize, we covered this journey from square root many queries all the way down to kind of the optimal number of queries while improving the prover time also, okay, over n. Right, so I only have 50 minutes to cover all of this, right? There's a lot of details which I skipped over, which some of the talks from today's workshop will cover in much more detail, right? So yeah, we should go to all of those. And also, like, there's a lot of details in the papers. But kind of this is a high-level summary of this kind of little journey that we've taken over the last 9 years. Okay, thank you.
Thank you, Pratyush. I guess questions we'll have to take offline. So Dan's talk is next, and we'll be in the adjacent room, not this room. Thank you. Yeah, good. Yeah, really nice. Yeah, yeah.
Test. Test. Receiving. Test. Uh,
Video is not important.
What's the video, brother?
Test. Test. Impostazioni. Wait. Test. Uh-huh. But not receive. Test. Test. Go to impostazioni audio. Oh, okay. Yeah. I receiving. Test. Test 1 2 1 1 1 1 1 1. Yeah, it's okay. Test. The volume is okay. A.
say anything, then it will just be I think we are ready to start. So I'm very happy to be introducing Alessandro Chiesa, who's a professor at EPFL. Today he's going to be giving a talk about something which we hope is close enough to something that interests you guys, which is about the recent line of work about getting very efficient proximity test from like linear code with minimal properties. Take it away.
Thank you, Giacomo. All right, cool. So it'll be a somewhat technical talk, so please, since it's a longer one, do interrupt me along the way, and I'll try to answer questions as we go, okay? So this talk is about IOPs. We've already seen them in the morning, so I'm just gonna flash the diagram, all right? So an IOP is an interactive protocol where the prover has oracle access to, so the verifier has oracle access to the prover's messages, okay? Why do we care about IOPs? They're essentially equivalent to hash-based succinct arguments. If you give me an IOP and even fairly weak hash function, such as a collision-resistant one, I can construct for you an interactive succinct argument. And conversely, if you give me a succinct argument based on ideal hashing, then I can pull out from that an IOP. Okay, somehow it's a very kind of fundamental object of study, right? And we care about hash-based succinct arguments very much for a number of reasons. They are post-quantum, and we've seen from today's talk from Justin that it's something that we should have and want to deploy. Okay. Today specifically, we'll also talk about the relaxation, interactive oracle reductions. It's just like an IOP, but instead of the verifier making up its mind, it produces another instance. And so this is basically a fancy word for a reduction aided by oracles from one relation to another. And from the perspective of this talk is just building blocks towards IOPs, okay? We'll kind of make our way slowly from some complicated relation to a simpler one, in particular a trivial one, by way of IORs, okay? Interactive oracle reductions. Again, so I think you've seen in Pratyusha's talk, some of you earlier today, a number of IORs, and you've seen how, at least on the quest of query optimal IOPs, how interactive oracle reductions play an important building block role, okay? So that's as much I want to say about these. I don't want to like belabor them because maybe many of you have sat through a number of talks about them. Are there any questions at this point before we move on? Should be fairly clear. Okay. All right. So the message I would like to kind of come across today is like, where do modern IOPs come from, right? We have like a stork here bringing a baby IOP. And kind of the established answer that we inherit from a line of work on probabilistically checkable proofs is that you arithmetize some well-chosen NP problem, maybe like circuit satisfiability or 3-SAT. And then, having arithmetized it, you locally test a resulting kind of property about a polynomial code. Okay? And to some extent, that's been the case well into the arc of research of IOPs, but I would say that at least at some high level, things look a little bit different today from this established answer. And maybe the way we look at IOPs today is a little bit more refined, where you kind of you pick a linear code, something quite unstructured. In fact, it could be even maybe a random linear code. And you pick some structuring operation. So this structuring operation could be something like interleaving or tensoring, and you just give a tiny bit of structure, and you obtain some kind of barely structured code. And you're gonna construct an IOR from your well-chosen NP instance to some encoded problem with linear constraints over this minimal structure, such as an interleaved code or a tensor code. And after that, you construct an IOP of proximity for this problem, okay? And what's the point of this refined answer is that, at least personally for me, this looks less more like an arithmetization and then a polynomial code, but more something that is like truly like kind of linear code native. Like there's barely any polynomials. We'll be seeing some multilinear extensions, but to me, it's like a bit of a far cry from the kind of algebra-intensive constructions that kind of we inherit from the efficient PCP literature, and then we feel the inertia of that in the first few years of IOP research, right? So I think we've kind of come in a different place right now. So today, I would like to have tried to distill from the last few years some maybe pedagogically simple construction of an interesting IOP purely from interleaving. And okay, I'll try to highlight that construction. I think it's just useful to keep in mind, and you can somehow branch out from there into, like, I think, maybe state-of-the-art constructions, using that one as a kind of a compass to kind of keep you grounded. Okay, so that's the plan. So any questions so far? Good. At some point, someone is going to have to ask a first question, right? So it's a safe space here. All right, so we're going to be working with linear codes. So let's just put it, I mean, many of you know what linear codes are. I just do this primarily just to get a common notation between us. Code is a subset of points in some kind of subset of vectors in some space. What is interesting about codes is that they have small, like the distance between any pair of elements in the code is bounded away from zero, like some sort of constant relative distance. You can imagine these balls around all these points that don't touch each other. And we'll care also about encodings. So there are two views of codes. You can either think about them as subsets or as like a procedure that takes a message and then maps into this subset. So we will care about encodings as well. So it's just some way to take a message space into that code. We'll care about linear codes. That just means that the space in which we're mapping into, it's an F-linear space. Think about it as some kind of vector space F to the D for some dimension D, finite dimension D. In this case, the minimum distance is just the minimum number of non-zero elements of any code word. And you've seen from Dan's talk the notion of list decoding is a fundamental property of codes. So for a given distance around a vector in the space, you can count how many code words are within this radius. So that's called the list, right, of this code up to a certain distance. If you go up to the distance of the code over 2, you can find at most one code word. And if you go beyond that, you'll find a few more. And one of the things that we've learned in designing efficient IOPs is that we have to make sure to work at distances where this list is not too large. Otherwise, we don't know how to design kind of protocols that are sound. Okay, so that's all the notation we're going to need about linear codes. It should be, I think, a good review, particularly for those of you who sat in Dan's talk. For relations, we're going to use standard notations. I'm going to go through I'm not going to go through it carefully, but you have relations. You can project to just the instances of the language, and sometimes I may care about fixing an instance and looking at all the witnesses for that instance. Okay? All right. Good. So now we get to, I guess, the start of the actual talk. All right? So my aspiration is to go through this blueprint. We're going to have two parts to this talk. In the first part, I'm going to explain what used to be in the old, let's say, blueprint for algebraic constructions, the arithmetization, but today I think it looks more like just a combinatorial encoding of the witness, okay? I'm going to show how, using an IOR, we can start from some well-chosen NP-complete relation. You can think about these as non-linear relations, because there's always some kind of either quadratic equation somewhere, right? And you start with an instance and a witness for this NP-complete relation, and we're going to create distance with like relying on any code. In fact, it doesn't even have to be linear, right? It just has to have good distance. Okay? This is going to make our witness, in some sense, even a little bit larger, right, to create this distance. But then, now we have some relation that is kind of simpler, okay? By way of this IOR, we'll end up with subproblems that are linear. They're not quadratic, okay? And so we'll have some encoded relation that involves linear constraints. And once we are there, we'll see that it's kind of quite easy to select a sequence of codes that gets smaller and smaller and have IORs that shrink our problem through operations that we'll see. And along the way, we'll barely need any structure of these codes, we'll just need interleaving. That's it. And to a first order, a lot of the kind of modern IOP constructions follow this paradigm. Of course, if you want to strive for optimality, for example, today we know how to get query optimal IOPs, not from interleaved codes alone, but we need tensor codes. But again, I don't want to talk about like optimal IOPs, I just want to get to like a respectable IOP that reflects the I don't know, the way of thinking of modern constructions, and that's, you know, a lot of interleaving, and kind of that's it. And that's kind of the beautiful thing, that it's a lot less algebra than we used to have. So I will probably spend maybe around 10 minutes, hopefully, on this part one, and then spend the rest of the talk on part two. It's an aspiration. Somehow I don't believe I'll be able to go through all of it, but I will try to go slowly, and at least for the parts that we do see, hopefully you will kind of learn something, okay? Are there any questions now? Still no. Please, there should be a question at some point. Okay, so that's the blueprint. Good. All right. So we're going to start with part one. We'll see a kind of transformation from an NP-complete problem to an encoded problem, okay, with linear constraints, okay? And kind of the main idea of this we often call this a preamble of the protocol, right? It's just kind of getting to the point where you can start really doing probabilistic checking. We want to create distance. Okay, so I want to define more precisely what are these kind of encoded relations that we're going to use. So this is not the relation we're going to use, but it's kind of a warm-up to it. So the kind of relations that allow for proximity testing are things of this sort. You have some message here called a Z. You encode it into a code word F, right? And you consider the relation consisting of valid code words of the code. Okay? Now, by itself, it's not a very interesting relation because it doesn't tell us anything about satisfiability of anything, right? So we need to kind of embellish this relation a little bit. So we can sort of encode and program into it some interesting kind of properties. So this takes us to another, I think, very elegant kind of basic relation is like the previous one, but we just add some linear constraints on the message. So again, we're going to ask that there is a valid message underneath the code word, but this message is not just anything. It's something that satisfies a list of linear constraints. How many? Well, for now, think about it as a constant, maybe 3 or 4. Eventually, we'll accumulate constraints that grow proportionally with the security parameter. But you should think about the number of constraints as not being too large, right? Something that you're willing to pay for in query complexity. Okay? There is no quadratic equations here. Intuitively, it is because we're going to shed them in that first preamble, right? We can get rid of quadratic equations and only survive with linear constraints thereafter. Interesting to see that such relations, deciding them is kind of is in P, right? Like, but nevertheless, we'll be able to reduce to such relations from NP using interaction. Okay, so this is our target. We want to sort of take our satisfiability problem and map to such things, and then for such things, we will construct IOPs of proximity. Okay. So in the instance here, X is gonna kind of keep track for us the specification of these constraints. So we have a vector Vi, that's kind of a coefficient vector, and tau I is the kind of target value, right? And kind of the question we're asking, is there an underlying message that satisfies, I don't know, 5 linear constraints for 5 specified vectors and targets inside the instance? Okay. I'm shoving under the carpet a couple of things, you know, for the experts among you. Like really, at this point, typically we work with ternary relations where we have an explicit instance, an implicit instance, and then a witness. I'm kind of hiding the implicit instance into the witness, whatever. Like, so if you look in the literature, you will find some kind of small mismatches. It's just, you know, for pedagogical reasons. Any questions? Yes? That's right. So I was exactly referring to the fact that typically it would be part of the witness, and you would consider what is here the witness as implicit input, okay? Yeah. So for now, I just kind of consider, basically, there is a dual view of proximity tests. Is the oracle given directly to the verifier an implicit instance or a witness? Like both are valid syntactically, it's just more convenient to make it implicit instance in formal treatments. For the talk, I'll be taking the view of the witness is eventually given as an oracle to the verifier. Okay, good. All right, so that's the target. The starting point is going to be some well-chosen NP relation. Unsurprisingly, it's going to be, for the purpose of this talk, R1CS, which I remind you are kind of this kind of well-structured quadratic system of equations. You know, matrix A times vector XW, matrix B times vector XW, take entry-wise product, and you get that kind of a matrix vector product. A, B, C, and little x are part of the instance, and big W are the witness, okay? And you know, that's kind of the picture you should have in mind. You have these matrix vector products, and the entry-wise product just means that I'm comparing, you know, the entry-wise product of the A and B kind of inner products, matrix vector products to the C one. Okay. Good, this should be like quite standard. All right, so the only polynomials we're gonna use in the entire talk are multilinear extensions. So there is this EQ polynomial, which is a low degree extension of the identity on the 0, 1 kind of Boolean hypercube. Okay, so you should imagine you have n variables x, n variables z, and this EQ polynomial has specifically value 1 on the diagonal where x and the x's and the z's have the same bit string value, and off diagonal it's 0 because they're not equal, and outside the kind of 0, 1 n cross 0, 1 n is just whatever, okay? And this one lets us talk about multilinear extensions. We'll talk about multilinear extensions of matrices. So a matrix, even a rectangular matrix with m rows and n columns, you can literally extend it with the corresponding EQ polynomials. Okay, all stand. Yeah. So this yi should be a zi? There is a y that could be a z, could be a y. At least it's self-consistent there. But yes, yes. Yeah, maybe I should have used y up there. I know this one here. Yes, this one should be a zi. Sorry. Yes, I was looking down there. Good. All right, I can fix something already. And it's a multilinear extension because you can, again, you can imagine in this sort of a rectangular world, U is placed onto this kind of 0, 1 m cross 0, 1 n, and then outside is whatever, right? Okay. Good. All right. So the point is that you can map R1CS into a collection 4 linear constraints quite easily, and then what you end up is with an encoded relation. We're just going to see it quickly, see the protocol, and move on. So you have these matrix vector products, and in particular, I can look at them as a multilinear extension matrix times vector, and this gives me a natural kind of linear constraint with an indeterminate, right? So I'm interested in matrix A, B, or C times vector Z. I can replace sort of the matrix with an indeterminate here, right? And I get that this polynomial, if I were to evaluate it on 0, 1 to the m, I would get exactly the inner product that I'm looking for, which is that matrix times Z, right? Why am I writing it as a polynomial this way? Because at some point I'm going to be using sum check. Okay, good. So it's just kind of a clear, yeah, I think I have it over here, that yes, this polynomial can be viewed as taking the matrix vector product and then extending, right? Okay. So why are we doing this? Because you can take the satisfiability condition of R1CS and write it as a vanishing condition of multilinear polynomials. Okay, you give me A, B, C, and Z. This relation happens if and only if this polynomial vanishes everywhere on 0, 1 to the m. Okay, these are all pretty standard kind of things that you should have seen before. We have a vanishing condition. That means that we can bundle it up using another EQ polynomial into a summation condition, which is a sum check condition. Okay? Any questions about this one? I think this is all, I think, basically any standard sort of kind of snark that uses some IOP behind it, even polynomial IOP, and if it's about R1CS, it's likely going to use some variation of this kind of setup. What's the takeaway? What we're about to do is that this setup is compatible with like basically any code. I don't need like any structure from the code to talk about it. So here's the protocol. So we see the protocol and we can move on. The prover will assemble the full vector from the instance in the witness. And then given any code, really any code, it will just encode that full satisfying assignment and send it over as a code word. That's an oracle. Okay? Actually, I think this is going to be the only oracle in this protocol. The verifier sends over some randomness for the reduction from vanishing to sum check. And we run the sum check protocol as a reduction on this claim. Okay? Why this claim? Because look, we were interested in this part vanishing on 0, 1 to the m. And so this one reduces that vanishing claim to a summation claim. And that's what we wanted to do. This sum check reduction yields a claim that says the add-end evaluated at a random point where you replace B with the randomness that the verifier injected into the sum check protocol will yield some claim of this form, right? This one, the verifier can evaluate by itself, and this one, it will need help from the prover, okay? So the prover will say, okay, yeah, you cannot evaluate these things by yourself. Here are the values, alpha, beta, and gamma for these three guys. The verifier will just check that claim, assuming those claims are correct. And now the verifier can just prepare what are the leftover now linear claims to pass on, right? So using the identities before, the coefficient vector that is relevant here are these three, which are known to the verifier at this point. It has the matrices A, B, and C, and can just write down these coefficient vectors. Then there is like a little technicality around the input consistency. I'm just going to gloss over that. Doesn't matter. It is in the slide for completeness. The point is that now we have reduced satisfiability of R1CS to a claim about an encoded message in an arbitrary code. I don't even need linearity. And these three linear constraints on the message and some other linear constraint for input consistency. So a total of 4 linear constraints. And so in here, when I look at a protocol like this one, I'm like, look, there's like barely any arithmetization here, and surely we're not relying on any property of the code, not even that it's linear, okay? In fact, the fact that it works for any code, you might ask, but does it even have to be a code? Where does it matter, right? So I'm gonna get to that in a moment and see exactly the point where the code comes up, because when you need the code to have property A, B, C, and D, it's kind of, okay, whatever, like, it needs 10 properties, so I can only use these codes. When you can use any code, then it will be like a very well-identified place where the code contributes and only contributes, right? Okay, any questions about this protocol? We're almost done with part 1. Good. Yeah, sure. Yes, so at least for this kind of a protocol, let me get there. The verifier has A, B, and C, and it can compute these, because of course it also has rows, so there's nothing that depends on the witness here. This can be done in like linear time. If you want to run in time that is sublinear in A, B, and C, which we do in practice, you would have to move these to a holographic kind of pre-processing stage, which is that, you know, you can also do, but it's a more complex protocol, but yeah. So like maybe let me add that I will not be like focusing on like a sublinear verification, but just on a kind of a bare bones kind of a good query complexity. Okay, good question. All right, so where does the property of the code come up? So it's pretty easy to prove that if the instance is not satisfiable, then no matter what the prover does, the probability that the output instance is not in the output encoded relation is bounded by order of m plus n over f. You can just see where the soundness errors come from. You have some soundness errors in bound link, the soundness error of the sum check, and the soundness error of the input consistency. Those are the only the only randomness of the reduction, and they each contribute some errors. This is not enough for local testing of the output claim, but what you can prove, and this is, I think, pretty amazing, that it really at a small price in error, you can prove a strictly stronger claim that if the original instance is not satisfiable, then you pick any distance you want, target distance, of course, again, against any prover, the probability that the output is delta far from any valid message that satisfies those constraints is at most that same probability blown up by the list size at delta. And here is like really a minimal, like very clear place where the code comes up, and the reason why you want the code is because in such reductions, what controls soundness is the list size at the distance you're targeting. And so what the distance contributes is that because we will eventually want the distance to be, let's say, constant or even very close to 1, having a good code is what keeps this list under control. Okay, and nowhere else. Like in this reduction, you don't need it for anything else. Okay, so I think that's what I wanted to convey, that you can take NP and convert it into like an instance of this encoded relation with linear constraints. And there is really no structure needed from the code other than, you know, being a code and having bounded list size. Of course, you can set the distance to be within unique decoding. This distance will be 1. You can also set it beyond it. It will be whatever it is, right? You just need to be able to afford it relative to m plus n over f. Okay, so we're about to transition to the other kind of part. Like, any questions here? To me, this is like a canonical modern reduction from NP to encoded instances. Like it kind of summarizes kind of the common core of kind of many of the IOPs that we have out there. Yeah, good question. Yeah, I don't see where it would come up also, yeah. I think this works really for any code. But I have to like, yeah. Yeah, I don't think so, yeah. Good question. More questions? Okay, good. So there's like interesting kind of optimization. Sometimes if you don't like list size times sometimes that one, you can add out-of-domain samples to kind of pull it out and kill it via separate out-of-domain samples. All right, so takeaways, we had NP, a well-chosen instance, and as ingredients, an arbitrary code, multilinear extensions, some check protocol, and now we have reduced the problem to local testing of sync-coded messages with linear constraints. There is all kinds of embellishments you can add, zero knowledge, holography we discussed. You You can start from other nice NP relations, and as long as they're like reasonable, you can sort of adapt this approach to some of these. Okay, good. So we've seen this part, okay, which is about creating distance. We haven't used much from the code other than the distance. And now we've landed over here where we have some linear relation with, in this case, we are starting with 4 linear constraints. And now we're not done yet, right? Like we have a problem to solve. And the approach in many constructions is to go through a sequence of iterations to make the problem smaller and smaller, okay? The nice thing is that each of those iterations are kind of small and cute, and you can sort of really understand them in detail, and you just then concatenate it, okay? So now, with the remaining 25 minutes, I just awarded myself 2 minutes, we'll see some of that, okay? And this is where we'll start using some minimal structure, specifically interleaving, okay? So I'm gonna go through a quick warm-up. I think Pratyush already went through it this morning, so I think I'll do it pretty fast. So remember, interleaving is an operation where you kind of stack code words and then you rethink the alphabet size vertically in these columns, right? So the picture is this one. You have an interleaved code word. So you have this factor of interleaving. You take the code and you kind of consider k code words stacked over each other, but now your alphabet symbol is like a column, right? Interleaving preserves linearity. And if you have an encoding for the base code, it gives rise to a natural encoding for the interleaved code where you just go by rows. Some people like to think of interleaving in the transpose way. I'm sorry. I think interleaving is totally stacking this way. I don't like hanging the code words next to each other because I can imagine they're dangling somewhere. Like this way, they're like, they're like on top of each other, right? But it's just big endian, little endian thing, right? So, all right. So if you don't have constraints, if you just look at the encoded relation with no constraints, going from an interleaved code to the base code is kind of pretty straightforward. So let's say that you wanted to design an IOR from a relation with no constraints over the interleaved code to the base code, which is like a smaller relation by a factor of k. You just do a random linear combination. And Dan gave a fantastic talk that talks about how you can relate distance about these original kind of interleaved code to the distance of these kind of derived linear combination, right? It's kind of not hard to see that if you're not trying to create distance, not being in the code will lead not being in the code with high probability, but it gets much more as a deeper question if you want to preserve distance. If you start out delta far from the interleaved code, you want to be bound the event that you drop below delta. Sorry, this would be greater or equal to delta, right? So start at least delta, then at least delta except for some probability. Another typo there. Okay, and this leads to the question of distance preservation. I don't really want to go over it. Dan went over it at length. Basically, it says you can define the property that you need to get that IOR to work. For that specific IOR, it's enough to have like a weak notion distance preservation, but in many other settings, you want this more. You want more mutual collateral agreement. Won't go through it. It's not the focus of this talk. The point is that we have such notions, we have such results, and the takeaway is that if you don't have linear constraints, kind of reducing the problem size is just a problem of distance preservation, and that's it. It's essentially equivalent to it, okay? And what I want to try to explain and convey is how can we reduce also linear constraints, which we have, right? Like we started from NP, we ended up to an encoded relation with linear constraints. So we have to be able to kind of shrink linear constraints as well as we go forward, right? If we go from an interleaved code to its base code, we also need to carry forward these linear constraints. And also, once you reach the base code, what do you do? And so this will lead to like a beautiful notion, code switching that kind of permeates a lot of the constructions of IOPs, right? And I think I have slides that sort of get to the point of each of these kind of core ideas in some sort of isolated, kind of pedagogically simple setting. Okay, so so we'll see now how to fold code and constraints, and then hop to another code. Okay, so that's basically the strategy of modern IOPs. Any questions about this? Yes.
So for the first part of the talk, you said that we didn't need to assume anything about the code.
Yeah.
For this part, you're assuming linearity.
Yeah, so for this part, we'll use two kind of orthogonal properties. So interleaving, we'll use it as a tool. Interleaving, by the way, makes sense also for nonlinear codes, right? And then linearity. Linearity is simply because once you interleave and you want to shrink, like you kind of need to have something to rely upon to shrink, even without constraints. If you just give me an interleaved code word and I want to kind of reduce to the base code, I'm already using linearity just for this, even before I hit constraints, right? What is, I think, surprising is that that's it. Like, nothing else will matter to get to the end of this, okay? Now, there are other things you might worry about, like the efficiency of the verifier. Is it linear or sublinear? Then maybe you need slightly more structured codes. But if you don't care, you just want good proof length and good query complexity, interleaving and linearity would be enough. Which, again, I think it's interesting to stand back and appreciate. To me, this is not the way we think of PCB constructions, for example, right? Or early IOP constructions. All right, so now we're back to local testing with constraints. All right, so I'm going to outline the strategy, let's call it fold and hop. So here's a strategy we're going to take to reduce the problem size. So we're going to start out with some interleaved code with linear constraints and rely on a IOR whose entire job is to reduce to the base code, okay, with the linear constraints. Now we're kind of stuck, right? In principle, we don't know where else to go. And the idea is to hop back to an interleaved code. So here we're shrinking the problem. Here we preserve the size of the problem. We're moving back to a structure that allows us shrinking further, okay? And this basic gadget just is repeated over and over, okay? Until you feel like it's enough and you just trivially solve the problem. You just ask the prover, send me the witness, I'll directly check it, right? So as you go through, your problem size may start, I don't know, at n, and then it goes to n over k1 because we're shrinking by a factor of k1, right? Across the hop, it doesn't get smaller, but then we shrink again, right? And that's how it works. We kind of accumulate these shrinking factors. Now you might ask, wait a second, like, why are we doing any hops? I could just pick my shrinking factor to be huge to begin with. There's a trade-off. And the trade-off is that your alphabet size in this IORs is going to depend linearly with K1. So like you have to read K1 alphabet symbols over here. You have to read K2 alphabet symbols over here. So you cannot afford blowing up these shrinking factors. Common settings are either constant, logarithmic, or square root, okay? Depending upon kind of your target. Further, because we'll be working with sum check, we'll assume that all the relevant quantities are powers of 2, but again, asymptotically, it doesn't really matter. But that's the strategy, and in a sense, the moment I give you these two mostly unrelated IORs, you can really like construct this in some configurable way, and that's it. That's how you construct an IOP of proximity for linear constraints. Okay? Questions? So the plan now is that we'll talk first about this one, and then if there's time, that one. But I think I will be able at least to talk about this one. Yeah? Now, some of the optimizations I'll briefly mention have to do with how to magically choose these factors as you go through, choosing the codes to make certain things happen with distances, right? And then other things that are have nothing to do with this specific structure has to do with bringing in tensor codes for special tasks. But that's for optimizations. I think this is kind of like the pedagogical core, I think. All right. So at high level, what we're going to do is do something like a random linear combination, but not quite. It will be like think about it as a systematic random linear combination. And that's something that we can call an interleaved fold. Okay, I'm going to define an operation for you. So I have some function defined that, over some number of field element of alphabet symbols. These are large alphabet symbols. Okay, so now I have little k. You should think about it as 2 to this little k is big K, but now it's a power of 2, so I'm making it explicit that it is a power of 2. So I have sigma to the 2 to the k, and I want to kind of shrink the alphabet size by folding around some field element. Okay, and this is the mapping. Okay, I don't want to go through it. I have like a picture for that. So this mapping, what it does is you take every location of the function, which can be seen as a vector because this is a large alphabet symbol, right? You take this large alphabet symbol, you disassemble it into 2 to the however many coordinates you're folding around. Okay, so this one is I field elements, so you disassemble it into 2 to the I pieces. Each of the I pieces will have size 2 to the k minus 1. And each of those pieces, you take this sum. Okay? What is that sum? We'll interpret it later. For now, it's just some other linear combination. Instead of being like kind of fully random, it's just some other coefficient vector that is related to Q. The role of a Q here is that somehow it's doing a sum in the systematic part of the code. Okay, and we'll see later how this one kind of matters. Okay, so that's like interleaved fold. So far, it just seems like some whatever operation. I will, I think, in the next slide, tell you, like, what is its properties. Okay. All right. So there's some nice properties. The first one is that it commutes with code encoding. I can fold an interleaved code, or fold first and then interleave less. And either way, I'll get the same thing, right? So that's nice. Another property is that it interacts nicely with constraints, okay? I can take some constraint, right? I can define, so you give me a target vector and a message z. I can define this multi-quadratic polynomial q sub coefficient vector and message. I can define this multi-quadratic here. And it has the property that the linear constraint of v and z can be expressed using this sum check-like claim. Okay? Why? Because. But the because fits here. Okay? I don't really want to go through it, but it's just true. Okay? And somehow the fold operation is chosen to make these things happen. Okay? That's what's special about it. All right? So we didn't have to consider something like this when we didn't have constraints because we didn't care about these other things, so it was enough to consider a random linear combination. Here we'll consider some other random-ish linear combination defined by EQ so that these things happen. Why do we care these things happen? Is because the next slide we'll see an IOR for shrinking or mapping from interleaved code with constraints to the base code with constraints. Okay, so these things are chosen to make that happen. Yes?
Do you need now that the code is systematic?
No, I guess I'm using systematic in an intuitive sense, but yeah, I think maybe systematic is not the right word. It's more that I've defined like a message space somewhere and I'm reasoning directly about the message space. But yeah, the code doesn't need to be systematic. Good question. All right, so just see the reduction. So what I want is I want to kind of do what I was doing before. Before we saw how random linear combination goes from interleaved code with no constraints to base code with no constraints. Now I want to do interleaved code with, let's say, one constraint for simplicity to base code with also one constraint. Okay, so I'm shrinking the code and the constraint at the same time. So look, we just argued that there's a certain sum check claim that is the constraint, so we're just going to run that reduction. Okay? So we run sum check on this one. Okay? That will spit out a claim that will say this multi-quadratic at a random point equals some value that comes out of the sum check protocol. whatever that is. And okay, if we go back to, so this one I can define as the new virtual oracle. Why does it make sense to consider this one? Because remember that folding commutes with encoding. So if I'm folding the encoding, it's tantamount to folding the underlying message, right? So therefore, it makes sense for me to define the coefficient vector on the target this way. Because remember, this guy was tracking the inner product of the folded message and the folded coefficients. So the folded message is secretly inside here. I mean, not secretly, but it is inside here, the encoding. I folded the code word that is tantamount to folding the message. The coefficient vector, I fold it, right? And the target is whatever the target is comes out of here, right? So that's it. That's my new constraint. And one can prove that if your original claim is delta far from a message that satisfies the constraint, then with high probability, so is the output claim. The high probability here curiously depends both on list bounds and on MCA errors, okay? That it shares very much the protocol, the properties that you saw, for example, in Dan's talk when he talked about this like elementary toy protocol that had a contribution from the MCA error and the list size. And the same thing is happening here. Notice that syntactically we are running a sum check protocol here, but from an analysis perspective, something much more interesting is happening because we don't just get the soundness error of the sum check protocol. That's not what's happening, right? You're getting some sort of kind of MC errors corresponding to the intermediate interleavings on the way to the base code, okay? So in my mind, I view this one as kind of the canonical basic reduction of an encoded problem with the interleaved code to its base code with the linear constraints, okay? All right, any questions? All right, so I have 6 minutes. I'm gonna skip over handling multiple constraints. The FYI is that it's not a problem. You just batch them. I wanna just conclude with the hop, okay? Actually quite simple. So let's say I have two codes. Let's say they're mostly unrelated. All I care about is that they have the same message space, okay? Because look, they have to encode the same thing, so they should at least have the same message space. And the goal is we want to, without shrinking, go from an encoded message with linear constraints to, again, encoded message under the other code with linear constraints. We may have a few more linear constraints, that's fine, right? We will need that C1 is linear. Anyway, C2 is going to be linear for other reasons later, but at least for this protocol, we need C1 to be linear. By virtue of being linear, we can write down a generator matrix for its encoding, right? And I'm going to need some notation to talk about its rows. So each symbol of the encoding of a message is a specific inner product between a row of the matrix and the message, right? That's what it means to be like a kind of a linear code. But also remember that because we may have large alphabet symbols, each alphabet symbol may contain, I don't know, D1 field elements. So I have a block of D1 rows that together construct the D1 field elements of that symbol. So I'm going to use this I, j pair to consider the ith symbol, jth location of that symbol. Okay, good. That's all the notation that I need. And the takeaway is that we can express every field element in an encoded message as a linear constraint. That's good, because this leads to a very nice, cute, simple protocol to go from code 1 to code 2. So here it is. So we're starting out with an instance under C1. So we have some message encoded under C1 with some number of linear constraints on it. What the prover is going to do is just send me an encoding under the second code of that message. Okay, so that's an oracle. What the verifier is going to do is to spot check linear constraints from F1. Concretely, we're going to have some security parameter t, think about it as lambda, sample some number of locations, read those locations from F1. Those result into linear claims, right? Like each of these symbols is intended to be a collection of D1 field elements that are supposed to be the inner product of this row of the matrix with the message. So I just write that row of the matrix into the vector. And I just carry those along. I have the original linear constraints and I have the new linear constraints corresponding to the spot checks. And one can prove that this works. It's distance preserving, okay? So for any delta, if F1 is delta far from anything under C1 that satisfies linear constraints, with high probability, this other thing is delta far from C2 to satisfy those other linear constraints, okay? And like before, if you don't like the product of list size and whatever is the soundest error, you can always break that relationship with some out-of-band sampling. Okay, it's just the same thing as before. Okay, that's it. So this is code switching. There's other sorts of code switching out there, right? That use, if you know a little bit more about C1, a little more about C2, then there might be other protocols you will be able to run. In this case, it's like a generic code switching. Okay. Good. All right. So I want to wrap up. I have 2 slides on verifier efficiency that I will not give. They have to do with basically what you do if you want succinct verification. So I'll skip over those and conclude. So if you are wondering about constructions that you have in your mind, how do they sit? In some sense, what we talked about is something that works with any linear code, with interleaving, supports linear constraints, and then we have, like, I've shown you how to handle list decoding. But it's mostly like extrapolating from a body of work that is showing a number of beautiful techniques for how to handle either constraints or no constraints, shrinking, but all of this with interleaving, right? So interleaving appears in important ways in many of these works. You've seen other talks where, I mean, there's also interleaving can be used also as a subroutine of a bigger strategy. Tensoring can also come in, but as far as today is concerned, this talk was just about how far can we go with interleaving and linearity alone. And the takeaway is that even with the modest structure of interleaved codes, you can get remarkably efficient and useful IOPPs. Okay, that's really, and I think it's an interesting takeaway. This looks not the way I was thinking about probabilistic proofs maybe 10, 15 years ago. But today, like, the things I described are extremely efficient and kind of really practical. All right, so that's the blueprint that we saw. Encoding using a generic code, and then assuming linearity and using interleaving to fold and hop, fold and hop, fold and hop, until your problem size is of something that you're willing to solve trivially. I'll put a side plug, which I mentioned also in the other talk, just in case there's a set difference. We're starting to do like a significant post-quantum expansion of ArcWorks, and happy to kind of establish further collaborations around that. And I think with that, I think I'm gonna stop here, and I'm magically on time. Yeah. Whoops. No, sorry, you mean this one? Yeah, you also have like a list coding. Okay, yeah, no, but I presume many of these, if you just sit down, you converge. Yeah. More questions?
I think just one question, so give me time.
Wait, what, sorry?
One question.
One question for... Maybe I just, okay, pass it back.
So all the linear constraints you're considering are always over the finite field. But in some cases, like our data is inherently in a group, like an elliptic curve group, for example. So does all this generalize to linear constraints over groups rather than just finite fields?
A good question. I think, so linear codes, you can lift them to be over modules, right? And so it could make natively sense over groups as well. And I think what would be missing at that point is having, I guess, MCA statements at that level of generality. I think if you were to get them, then I don't see anything that would specifically break here.
It's interesting, by the way, SumCheck easily
Easily
generalizes to that.
Yeah, I think it's just MCA, it doesn't seem. Look, for the best statements about MCA, I mean, I don't know whether they generalize, but at least the ones that we have about linear codes, they seem maybe they would go up to 2 modules.
I see.
Yeah.
Cool.
Yeah. Thanks for the question.
We're going to start again here very soon, so please don't go far.
In the building or in the room? Yeah, in lunch. Okay. A couple of years ago, nowadays is a PhD student at Harvard, working with Madhusudan, and I guess a little bit more, even more coding theoretic perspectives. And she'll be telling about sort of a line of work, in particular our latest work. What happens when you sort of think about... Do you like a Mandona? No, no, I'm good. Yeah. What happens when you consider a small field? Particular Boolean fields, Boolean circuits, and sort of recent work around that. So take it away, Nora. Actually, maybe, do you want this or do you want the Madonna thing? You good?
Okay, so thank you, Ron, and thanks, organizer, for inviting me. Yeah, so about IOPs, I will not go into. We've heard enough. This is based on works of and a joint work with Noga Ronsvi and my wonderful previous advisor, Ron. Okay, so in this talk, we're going to focus specifically on prover efficiency and in different ways to define prover efficiency in IOPs. So before we get into that, let's just start with like, what do we know about these things? So the first IOP, or the first PCP, had a prover that ran in exponential time. Then, with some advancements in PCP, specifically with the PCP theorem, the provers started running in polynomial time. Then we had a lot of advancement in specifically IOPs, leading up to provers running in nearly linear time. And now at this point, the distinction between linear and near linear IOPs already highly depends on the exact model we're working with and what exactly are we counting when we say linear. So this talk, we're going to focus on prover efficiency, specifically the prover overhead between computing and proving, in sort of the most strict model of when we say linear versus nonlinear. And we'll talk about minimizing the number of rounds, which can have a lot of practical implications. So the talk overview is going to be the following. We'll start by defining the model, the efficiency measures. Then we'll see a sumcheck-based protocol, which will have a quasi-linear prover and a logarithmic number of rounds. And then we'll sort of work our way into reducing the prover complexity and then reducing the number of rounds. Okay, so what is our computational model? So we start by thinking about whatever computation we're trying to work on as a circuit. And let's say the circuit has some size S. So then we want our prover to also be a circuit, and we're asking what's the size of the prover's circuit. So obviously it has to be at least S, but hopefully it won't be too much more than that. Specifically, we're going to also be focusing on Boolean circuits. So why circuits? Well, we could talk about like runtime instead of prover size, which often has a lot of correlation. But then with runtime, we start asking what kind of operations we're allowed and what kind of memory access. So circuits just give us like a more sort of clear view where everybody's on the same page. Now, why Boolean circuits? So for a couple of reasons. First of all, some computations just come as a Boolean circuit themselves, for example, like hashing. And then for that, we also want our prover to be a Boolean circuit so that we're not sort of comparing two different things. So just that we compare the same thing, we want them to be Boolean circuits. But also, if we're talking about arithmetic circuits, then we go back to the same question of over what field, right? So you can think of it this way. If I'm saying I can take this wall down in 1 hour, you really should ask me, do it with what? So if I say I can take it down with this small hammer, then it's one thing, but it's much easier to do it with this big hammer. So you can think about it as Boolean circuits versus arithmetic circuits, where the Boolean circuits are like this tiny hammer, and the arithmetic circuits are a bigger hammer the bigger the field gets. So for this talk, we're focusing on computation as a Boolean circuit, a prover as a Boolean circuit, and we will want our prover to be linear in the size of the computation, which is a line of work that started with the Noga and Ron's first work of this. Now, some of the snarks you might know have a linear prover. So what is so different about this? Well, they have a linear prover, but it's linear in the number of field operations. And they don't really account for the field operations. So here we're also like counting these field operations inside our complexity measures. And we will see later on how this makes things a bit more challenging. Maybe not a bit. Okay, so the second thing we care about is the number of rounds. And the reason we care about that is, so usually in IOPs, or the arguments that the IOPs are, or the arguments that are using these IOPs, in each round, a lot of the work can be done in parallel. But between rounds, we can't really do any parallel work because the prover sends a message, and then it waits for the verifier's coins before it can start the second round. But then you can say, okay, we're running fiat shamir anyways and everything, there's one round, the prover's not waiting for anybody, and we're happy. The problem is that even if there's no verifier, the prover is still simulating the verifier, which means that it still has to hash the function to get the coins, and only then it can start the second round. So either way, with or without fiat shamir, the number of rounds will have a lot of efficiency implications. Okay, So hopefully now I've convinced you that we care about these two things, being the number of rounds and the proving overhead, specifically in this like Boolean circuit model. So unfortunately, there's some trade-off between the two. So if we have a circuit that is like the original computation is a Boolean circuit of size S, what can we say? So for one round, aka a PCP, we can only get a superlinear prover. In fact, we only even have a superlinear proof size. If we're happy with a constant number of rounds, then we can take down the proof size, the proof length to be linear, but the prover still has to run in superlinear time or size. If we're okay with a much bigger number of rounds, a logarithmic number of rounds, then we can finally have a linear prover. And the question is, if we insist on linear prover, what can we get anything less? Well, what we'll see today is that we even can get a log star number of rounds. You haven't seen log star in a while, I bet. Okay, so finally, we're ready to sort of have a theorem here. So for every nice Boolean circuit of size S, there exists an IOP where the prover is linear in the size of the circuit. The verifier runs in polylog time. There are an order of log star number of rounds and an order of log star query complexity. So before we get any further, what is this nice I'm hiding here? So nice, I mean sort of like regular circuits or circuits that have a lot of repetitive structure. You can think of it as like doing some batch computation. So for the protocol we'll see today, we'll have a constant soundness error, but you can get a 2 to the minus lambda soundness error with paying an only polylog overhead, where like the trivial thing of repeating would give you a lambda overhead. Now, if you really want all circuits and not just these nice circuits, then we can also do that, but then we have to pay in a linear verifier preprocessing. And if you really care about the factors I'm hiding inside, then it's like specifically 2 log star plus some constant. So in case you haven't seen log star in a while, this is just the number of times we have to do log over a number to get it to be at most 1. And here are some examples. And why did I put this huge example here? Well, because this is way bigger than the number of atoms in the universe. So really, you can think of log star as just being bounded by 5. Okay, so we'll start with some more technical things. So any questions before that? Right, right, yes. Or for all I know. Okay, so our key ingredient is going to be an IOP for inner product. And I guess we've seen inner product come up, so maybe this doesn't surprise you too much. So what do I mean by that? Given x and y, we want to prove that their inner product is some value. Now, the verifier can just go ahead, read them both, multiply every index, sum up, and do everything. But we want the verifier to run in sublinear time. And the verifier has oracle access to some encoding of x and y. And what do I mean by encoding? We'll get to that later, but we've also seen error correction codes already, so this is what we mean. And why is this useful? Well, if we have that, if we have a linear prover that can prove this, then we can get a linear prover for rank 1 constraint satisfaction, which will give us IOPs for nice, or for specific rank 1 constraint satisfactions, which give IOP for nice NP. Okay, so proof outline. Inner product check really, really sounds like sum check. So let's go ahead and do that. And I won't get much into sum check, but let's kind of see why this is useful. So what is sum check? We have some low degree polynomial over some field with m variables, and we want to prove that the sum of this polynomial over the n-dimensional Boolean cube is some value. So the protocol that does sum check has this, where v has oracle access to the polynomial, and at the end, v only queries 1 point in the polynomial. So why is this really useful to us? Well, we have our 2 strings that we want to run the inner product on. We can turn them into functions. So this, I'm just going to be moving between these strings and functions, but really they're the same thing. The only thing that we kind of want to remember here is that when I'm moving from this to this, that m is just going to be log n, which is going to come up later. And then instead of looking at these functions, we'll look at the polynomials that are multilinear extensions over f of these functions. So we've also seen this, but just quickly to say what this means. So we want these polynomials that evaluate over in the entire field, but specifically on the Boolean cube, they agree with f and g. And because here for f and g, every variable has only 2 values we care about, then we can get these polynomials being multilinear. And finally, we can multiply these 2 polynomials. If they're multilinear, their multiplication will be a low-degree polynomial, and we can just run some check on that. Sounds very promising, but there are a few problems with this approach. So the first problem is that really the trivial way sort of to run some check only does not give us a linear prover. And again, by linear, I mean as a Boolean circuit. The second problem is that for the sumcheck protocol, we need V to have oracle access to Q. Now, one way to do this would be just that before we even start the protocol, the prover will encode the polynomial and send it, but this also has too much complexity. The prover doesn't have enough time to do this. So that's our second problem. And our third problem is, remember when we said that m is just going to be log n, so these polynomials will have m variables, which is log n, and the round complexity of the sumcheck protocol depends on the number of variables, which means that we will have a log n round complexity, and I promised you log star. So these are our 3 problems, and for the rest of the talk, we'll sort of tackle them one by one. Any questions about this? Okay, great. Okay, so let's start with the prover complexity of sumcheck, and you're probably used to thinking that sumcheck has a linear prover complexity. So let's understand why in this model it doesn't, and then how we solve this. Okay, so we know what the sumcheck protocol does, and let's sort of just a bit get into how it works. And we want to keep in mind 2 things: the prover complexity and the soundness, which we'll analyze later on. So how does the sumcheck work? We have this polynomial that we want to evaluate over the Boolean cube. So the prover goes ahead and evaluates basically almost everything. So it keeps the first variable as a variable, but then it iterates over all the other variables for all the values, sums up everything, and sends this new polynomial to the verifier. Now the prover has done most of the work. So all the verifier needs to do is sum up q1 of 0 and q1 of 1 and make sure that it's this value. But also it doesn't really trust the prover, so it wants to check that q is the right polynomial. Now, if the prover sends a wrong polynomial, then these 2 polynomials are different, so they disagree on a lot of points. So if the verifier just checks 1 point, with high probability it would catch a bad computation. So the verifier can just choose 1 point it wants to check. So let's say the verifier wants to check q1 of R1. Well, what is that? What is q1 of R1? It's basically fixing the first variable, but then summing up over everything else. So if we do that, then we just have 2 polynomials with m-1 variables, and we're back to our original problem. But that's fine, because we've reduced the number of variables, so they can just do the same thing and recurse. So they do the same thing, eventually leading up to the verifier wants to query this 1 polynomial in Rm, but this is basically the first polynomial at R1, R2 to Rm. Okay, but now it has queries to f and g, multiplies the 2 things, checks, and everything's fine. Okay, so we want to talk about the prover complexity versus soundness here. So we saw what happens at round 1, but at round t, the same thing basically happens. So at round t, we've already fixed the t-1 first variables. The tth variable stays as a variable of that polynomial, and then we sum up over everything else. So for the m-t variables, we basically have to give them all like 0, 1 possible evaluations and sum up over everything and multiply and so on. So we have something like order of 2 to the minus t field operations. Now, I'm kind of here ignoring the fact that the prover is going to also have to evaluate these polynomials. The prover doesn't have access to the polynomials, it only has access to the functions. So at some point, it needs to extend them to polynomials. But I can demonstrate the issue without accounting for this. And also, this is not a big cost here, but keep that in mind for later. So we have 2 to the m minus t field operations, which means this is per round, which means that this is the sum. Now, this thing converges to 2 to the m, and remember 2 to the m is just Rn, so it's linear, so it seems that everything is linear and we're happy, only this is linear number of field operations, so this looks more like this. Okay, but not all hope is lost. If our field is a constant size, then this still converges to 2 to the m, and everything's fine. Okay, but what about soundness? So where is our soundness coming from? So at every step, the verifier is checking these polynomials. And we said that if they're 2 different polynomials, then they can only agree on a small number of points. So the soundness error is coming from me choosing the specific point that they coincidentally agree on. But how many points can there be? Well, there can be d points, which is the degree, over the number of fields. So this happens every round. And for all, if we accumulate this error for all rounds, this is m times d over f. Now m is just log n, which means that if the field is a constant size field, this is meaningless. So to have any meaningful soundness, we need the field size to be at least m, which is at least log n, which then means we will be paying something like log n. So not linear, right? Okay, so if you were happy with arithmetic circuits over some large fields, then the sum check is linear and we're done and we're happy. But we promised Boolean circuits, so we're not done. So we have these 2 constraints, and they're kind of colliding, right? Like if we want good soundness, we have to choose big fields. If we want good good prover complexity, we have to choose constant fields. So it seems that really we can't get the best of both worlds. So what do we do at times of conflict? We compromise. We start with a small field, and then we have the fields grow bigger. So why does this help? So the thing about the sum check protocol is that at every round, the prover is working on a smaller problem. Or if you remember, if you just look at this sum, the number of operations on the field it has to do in every round gets smaller and smaller, which means that at every round, we can afford to do our operations with bigger fields. And for soundness, this is also fine. If we start with a field big enough, a constant, but big enough, we can sort of also grow these things nicely. So any choice of something of the order of these fields should work and satisfy the 2 constraints. But we'll see later on for the log star stuff that we need something more specific. Okay, great. So any questions about this part? Okay, so we've solved the issue of the prover of the sum check protocol. But now, so the prover ran in as a linear Boolean circuit, and we're happy. But at this stage, the verifier wants to check 1 point in the polynomial. And we said that sending the polynomial is too expensive for the prover. So the verifier doesn't have access to this polynomial. So this is a problem. And in order to solve that, we kind of have to take a detour into error correcting codes. So we talked, previous talks have mentioned error correcting codes, but we kind of want a specific perspective. So let's go ahead and define these things. So what are error correcting codes and why are they useful? So they come up in a very different setting. In a setting where we have Alice that wants to send Bob some message. But they're sending it over a very noisy channel, or well, not very noisy, but slightly noisy channel, where some of the bits can be flipped. And so then Bob won't know what Alice wanted to say. So instead of just sending the message, Alice will send some function over the message. And we call this function a code, where this function takes a string of size k and outputs a string of size n. And the property we want is that if we look at two messages, then their code words are going to be very much far apart. And by far apart, I just mean that they don't disagree on a lot of the points. And why is that helpful for us? Well, if they don't disagree on a lot of the points, and a small number of points are flipped, then Bob would still understand which original message this was coming from, and would still be able to sort of correct and understand the message. So one thing we really care about in codes is the distance, and the distance is just the minimum over all 2 pairs of code words of what I just said, which is like the number of disagreement points. So the bigger the distance, the better. Another thing we really care about with codes is the rate. So the rate, you can think of it basically as like how many messages, how many bits of symbols of information I intended to send over the number I actually end up sending. So we want these two to be as close as possible. And finally, we care about encoding complexity, which is how long it takes Alice to like compute the code word of her message. So one example is multilinear extensions. These are codes, and the way to think about them as codes is that we have a message. So the code word would be the polynomial that agrees with this message on the Boolean cube. And the distance for these codes follows from the fact that 2 polynomials of low degree cannot agree on a lot of points. So back to our proof setting, and why is all of this helpful? Well, we can think of our messages as sort of computation, like a computation that the prover is doing. And so if the prover sends the code words of these computation, and the verifier is trying to figure out whether the computation is right or wrong, then if we have the wrong computation, the code word of the wrong computation is very far apart from the code word of the right computation, which means that just checking a small number of bits in that computation would help the verifier understand if it's the right or wrong computation. And if there's a mistake, with high probability, it will still catch the mistake, even if it doesn't read the entire thing. So from that, it's obvious that the distance of the code is going to relate to our soundness. The rate usually relates to our proof length, and the encoding complexity is just the prover's work. So it's going to be relating to the prover complexity. So why is all of this helpful for us? So turns out there's nothing really special about polynomials, and we can run some check on any tensor linear code. So what do I mean, tensor linear code? So linear code, and I feel like I might confuse you here. Now this is not runtime, not complexity, not nothing. It's just the fact that the map of that code is a linear map. And tensor, it doesn't really matter, but it just has like a nice structure. But almost all of the codes we think about are linear codes, and if you give me a linear code, I can construct a tensor code out of it. So we have these codes, and we're happy. So what do I mean when I say we can just run some check on them? So I mean that if we have a message that we want to sum up, we want to like prove the sum of, then we can do something very similar to the sum check protocol, where at the beginning, P sends the code of this message, and then they run something like sum check, and at the end, instead of querying a point in a polynomial, the verifier queries a point in the code of that message. And basically, in the run, everything, like they're not sending polynomials, they're sending code words. And so instead of having this notion of 2 polynomials can't agree on a lot of points, we have this notion here of 2 codes cannot agree on a lot of points. But everything else works out basically the same way. So why is this helpful for us? Because although polynomials cannot be encoded in linear time, which means that given a message, we cannot write the entire polynomial in linear time, other codes can. So let's try a second attempt at this. So we have our x and y, and now we convert them into code words, ex and ey, and the prover now can just do this with linear time and send out the code words to the verifier. And we use a linear time encodable code. We know that these exist and are linear, and everything's linear as a map, and we're happy. And then they just run some check on ex, pointwise multiplication, ey. Don't take a picture yet. This is not going to work. Okay. So what is the problem with this? Oh, and at the end, V queries the points, whatever.
This sum check is not that sum check, right? It's the sum check from before?
It's this sum check.
It's not the previous sum check that you described it?
I mean, it's the same sum check as before. Sorry, it's the same sum check as here, which is on this new code that we have. Only the problem is that this might not be a code word. So I said nothing is special about polynomials. In fact, there is something special about polynomials. And what's special about polynomials is that if you multiply 2 polynomials, you get a polynomial. And if we think of polynomials as codes, then if we take two messages and pointwise multiply them, and we take their two code words and pointwise multiply them, something nice happens. This is not true for every code. And we don't know of any linear time encodable code that has this nice property. So if we had this linear time encodable code that has this property where we can just multiply the two code words and then run some check on them, then everything would be nice, but we don't. Does this answer your question? Okay, great. Okay, so once again, we have a problem. We have two nice codes. Each of them has one nice property, but we kind of want to get the best of both worlds and mix these two properties. Any ideas come to mind that possibly we've heard about twice today? So we do code switching, which is basically getting the best of both worlds. Okay, so now this is really the proof outline. So we have a claim on some inner product of x and y, and then we run some check. Now back to our normal sum check polynomials, everything's fine. And then at the end, the verifier wants to check one point in the multilinear extension of x and y. So instead of doing that, it just produces a claims on these things, so this part is basically an interactive oracle reduction, right? Okay, so it wants to now prove claim, or it wants to be convinced of these two claims on x and y. And now we do code switching, which is basically generalized sum check. It's sum check with some coefficients. And instead of that, at the end of it, the verifier will check 2 points in the encodings of x and y. Okay, so I said before, we can't really run sum check on these, like the way we wanted to run sum check on these new codes, it doesn't work. And now I'm telling you, we want to run something that's even more general than sum check. So what's happening here? So why did we even bother with the first part? So the really nice thing about the first part, it sort of separates the claims about x and y. So what we gain in the first part is that now we have a claim on x and a claim on y, and they're separate. And so now we can use this nice code that might not be multiplicative. And we're running what they need here is one single point of the multilinear extension of x and y. Okay, so the first part we've seen how to do, right? So now I only owe you the second part. Questions about this? Okay, great. So eventually the first part is going to take log star rounds, and the second part will just be a constant number of rounds. But why is it log star? Right, exactly. Great question. So it's not yet. It's now the first part we only saw log n rounds. Okay, so for the second part, you can think of it just as a polynomial commitment scheme. So if we look at this entire thing, basically the prover starts by sending this like encoding of x and y, and you can think of it as a commitment to some polynomial. And at the end, where the verifier wants to query some point of this polynomial, we can think of the second part as just like opening one point in that commitment. Okay, so finally we can get our theorem about specifically IOPs. So we have x and y, where P has access to x and y, V has oracle access to EX and EY for some linear time encodable code E. And then we have an IOP proving the inner product such that this we've seen, the prover is linear, they're an order of log star rounds, log star query complexity. Oh, sorry. Okay, so for now, let's start with this part, which is just the log n. So for the log n, we had an outline where we do first a reduction, do some claim on the MLE. This part we've seen, and then from MLE to the second code. How am I doing on time? Okay, so this part is a result, is a previous result of Ron and Noga. But the protocol we saw, or the outline for the protocol we saw, is actually much simpler. So in the first result that achieved this, they did code switching after every round of sum check. So you do one round of sum check, code switch, one round of sum check, code switch. And the protocol we saw just does the entire sum check and only one round of switching at the end. And it will be really useful for our log star round, so that's why I showed it. Okay, So this half we saw. Let's talk about the second half. And okay, yeah, I think we're fine with time. So we want to do code switching. So let's have this more specific. So we have some function f, where p has access to f, and v has Oracle access to the encoding of f. Then there's an IOP for proving some point of the MLE, right? This is what we want. It's for a nice point, such that the prover is linear. There's constant number of rounds, constant query complexity. So what is this nice point? Yeah, so this just means that the point is coming from these growing fields. So this is weaker than if I didn't say nice point, but we don't mind much because we know that our first reduction is going to anyways produce this nice point, so we can just use this one.
Sorry, what exactly is the definition of nice point?
Okay, great question. Yeah, so the definition is just that it's coming from these growing fields that satisfy the two soundness and complexity constraints we saw before. There are a few fields that we can choose different types of growing fields that satisfy this, and so any of them is a nice point.
Maybe first thing, what is a not nice point, and then it would help clarify.
Okay, so a not nice point is if we have that, so this point has like R1, R2 to Rm. So a not nice points would be all of these things coming from a constant field, because then we don't have any soundness. Or a not nice point would be that all of these points are coming from a non-constant field, because then the prover complexity would be too big. So a nice point is kind of starting with the constant size field and then growing so that we have a balance between the soundness and the prover complexity. Great. Any more questions? Okay. So turns out it's not even trivial to compute a single point in the MLE with linear time. So, let alone proving. So why is this still possible? So the way this is done is that we sort of extend the polynomial one variable at a time. So we can think of it the following way. One point in the MLE is just linear combination of the original function, right? But it's a linear combination with really nice coefficients that have a very nice structure, which allows us to if you recall how we define these with this, I think we saw the equation before. It was equality and so on. So there's a very nice structure of these coefficients, which means if we extend our polynomial one variable at a time, and then sort of reuse the work we did in the previous round, and use one more fact, which is that we have these nice points that are coming from these growing fields, then with all of these together, we can still get the linear prover. Okay. So the proving part is very similar to computing. So basically, we can think of it this way. In SumCheck, what we're doing is that we have a message and we want to compute the sum of all of its elements. Here, we have something similar. We have our message and we want to compute a point in the MLE, which is a linear combination of these things. But it's not any linear combination. It's a linear combination that has a very special structure of the coefficients. So when I said we can do SumCheck on any other code, basically what we're doing here is that we're doing something very similar to SumCheck on this new linear code that we have. Okay. Any questions about this? Okay, great. Okay, so the two things we wanted in the beginning, we did. One last thing that I didn't tell you what to do is how to reduce from log rounds to log star. So let's kind of remember where is this log coming from. So we started with our string, and then we turned it into a function, which was on 0, 1 to the m. And we said that, okay, in this case, m is log n, and SumCheck has the m rounds. And this is where the bad rounds coming from. Okay, but we don't really have to use this specific type of structure of function, right? We can use any function. We can use a function that looks like this, where hi's are just any subset of the field. Okay. So ideally, we want our L to be a constant. to make our L a constant, then hi would be something like n to the 1 over L. So one problem is that we cannot, the sort of the polynomial that agrees with this thing is no longer a multilinear polynomial, because the reason we were able to have multilinear polynomials is that every variable had two optional values. So here every variable has n to the 1 over L values, so we can't do multilinear, but that's not really a problem. We can do low degree extensions and everything, and like sum check works on low degree, and everything is fine. So that's not an issue. The other issue is that even in the first round, the prover size, because of like sort of this extending like the function, has this complexity. But this is if we do it in the trivial way. So if we do it in a slightly smarter way using FFTs, then we can get, for the first round or all of the rounds, n times polylog n. Not too bad, but I promised you really a linear prover. So still not good enough. So this is why we can't get constant. And so once again, we have this problem. If HIs are like constant size, then we can get the prover to behave nicely. But if the HIs are not a constant size, then we can get a constant number of rounds. So we have this trade-off between rounds to linear prover. But you've seen this before. So what do? Yeah, we start with a small HI and then we grow them. Okay, so this time I will not write the constraints because they're too ugly, but I will just tell you the following. So remember where we had, I'll go back. We had this n polylog n. And so this means that at every round, sort of, this is what we're extra paying, which is why between every round, this is the growth that we can have. So this 2 to the hi minus 1 kind of translates to this, comes from this polylog n. So this is the way these things grow. And then what is L if this is the growth? Exactly, it's log star. Now, it's not really log star because these don't grow so nicely 2 to the side. It's like 2 over something. So this is why we get 2 log star and not log star. But basically, this is the idea. Great. Any questions? Right. Yes. Ron still let me finish my thesis without without that part. Okay. Great. So our main result, all right, never mind, was IOP for regular Boolean circuits where prover size is linear and we have log star. So the open questions were, can we get the same result for all circuits and not for these just like regular circuits? So we said yes, but then we pay in verifier time. So can we do this without paying in verifier time? The second question is, can we get this with a constant round IOP with a linear prover? And we don't know that this is true even for arithmetic circuits over large fields and not just Boolean circuits. So one way to solve this question would be to have these codes that do it all, that are both have this multiplication property and have this linear encoding time. So if we had these codes, we can get, even in Boolean circuits, the constant number of rounds and the linear overhead for the prover, but we don't know if these codes exist. Possibly with other directions, you could also do that. Okay. Yep. So thank you very much for listening, and I'm happy to answer questions. Right, so, okay. Hopefully I have the right statement of theorem. So, okay, never mind. So for every circuit, there exists a prover and verifier. So the circuit is sort of encoded inside the prover and the verifier.
If you're asking from the verifier's perspective, then think of offline preprocessing that reads the entire circuit. It stores only an oracle or whatever, and
I mean, we don't know of any codes that are R, but we don't know that there can't be a code that is both things.
So what's the obstacle there? Do we understand what the obstacle is? We don't know.
Maybe I can add that, like, so linear codes are a dime a dozen. Multiplicative codes are very rare, and they're sort of coming from algebra, essentially either polynomials or fancier versions like AG codes. And like the number of multiplicative codes that we know, especially like efficient, are basically polynomials or AG codes. So we don't have, that's sort of a structural challenge. Yeah.
What about the round-the-robin soundness?
Here, yeah, this should have like, right, basically all we're doing is sum check.
But maybe, so I think Noor was focusing on the constant soundness regime anyway, so it's not like super relevant. I think she mentioned that there's a work by myself and Justin Holmgren, which upgrades the soundness at like better cost and repetition. And you can also ask here what happens with repetition. One observation sort of is that you might say, you know, here we have like a constant error, like in the first round in particular, we won't have like better than constant round by round soundness error in the first round. Even without the fancy thing with Justin, if you repeat, you seem to run into a problem. But actually, if you think of it, it's kind of okay to have like constant round by round, like when you do repetition, you have constant soundness error in the first round, but then it's gradually reducing. So if you think you do like lambda forward repetitions, in the first round, like half will die. Next round, like only half of the remaining will die, and so on. So yeah, can discuss more offline. More questions for Noor?
I'm just curious about state-of-the-art theory. Do we get a complete round complexity? Say I want a 2-round IOP. What's the best that we know in terms of root size and all?
Do you care about verifier size?
Sure. Yeah, I guess that's a good thing.
I think like all of the concretely efficient things are either running sum check or fry or a combination. So all of them have log n rounds hiding somewhere. And in particular, the cost of running stuff like this is that you need to send kind of like multiple largish oracles. Doesn't seem like maybe the best idea in practice. Please.
So can you have kind of a hybrid that doesn't actually get you log star asymptotically, but you kind of, so there's the HI are increasing, but then you have a cutoff so that you're not using one for the 2 line. You see what I mean?
Yeah, I think as a matter of fact, we do have a cutoff that the HI is at some point, like it's the exponential growth you can only do, and at some point we do have a cutoff.
Yeah, so the reason is that when you don't have a cutoff, like the last notch is very, very long, and so.
So once you get to like sort of polynomialish size, then you want to kind of like end it there, because from here on it's only going to be a constant number of rounds anyway.
I see. So you don't actually want them to increase exponentially.
You want them to increase exponentially up till you get to like say square root n or something, or like n to the epsilon, and then from there on just like keep it at n to the epsilon and do like 1 over epsilon rounds. Yeah. Great questions. Okay, so let's thank Noor again.
And we'll be back here in 20 minutes at 4:10. Or 5.
Okay. All right. Hey, folks. Everyone get settled. All right. So this is the last talk of the day of IOP Fest. But do please stick around after this because we'll have an open problem session. So please bring your open problems, and you know we'll chat about what the future of this field is going to look like. So we're very fortunate for the last talk to have William Wang, who is a PhD student at NYU. Are you second year, third year? Third year, okay, with Benedict Bunz. And he's going to tell us about sort of recent direction in understanding proof systems. We heard a little bit about these already, these interactive oracle reductions, and now we're going to hear a lot more. So William, take it away.
All right, thank you. Actually, before we start, can we close that door? I mean, does it open or is it locked from the outside? Okay, so great. Okay, so today I'm going to talk about interactive oracle reductions. Again, we've seen these throughout the day. So what I want to do for this talk is sort of give more precise, like more mechanical definition, and then briefly we can look at how IORs are used to construct IOPs in a modular way. And then sort of we'll shift our focus to the main point of this talk, which is how can we use interactive oracle reductions on their own to build more lightweight proof systems. Okay, great. So first of all, just so that we're on the same page, what do I mean by a reduction? So typically when we want to prove a statement, we try to reduce it to simpler and simpler statements, and until they're simple enough that we can just decide them on their own. So let's say I have some statement A. I'm going to first reduce this to some smaller statement B, and then to C, and then maybe the verifier themselves can just decide C themselves. So this overall process I refer to as a proof, and then like some individual step in the process, moving from one statement to another, I refer to as a reduction. Okay, so before we define what an interactive oracle reduction is, let me first define what just an interactive reduction is. Okay, so there's a prover and verifier. They want to test some membership claim in an NP relation. And the prover will receive the instance and witness. The verifier will receive the instance. They'll talk back and forth. And instead of deciding the membership, the verifier is just going to output some new instance. And the prover is going to output some new witness. And intuitively, the goal of this proof system is to reduce the membership claim from the old relation to a membership claim in a new relation. Okay. And completeness and soundness are fairly straightforward. Completeness says if the original instance and witness were in the relation, then the new instance and witness will be in the new relation. And conversely, soundness says that if the old instance was not in the language, then with high probability, the new instance will not be in the new language. Okay. And so a natural question to ask is whether we can make such a reduction succinct. And throughout today, we've seen that a very nice way to sort of frame this question is to move to a different model of interaction, specifically an interactive oracle setting. Okay, so this is sort of the, if I told you, okay, here's an interactive reduction, oracleify it, this would probably be the first natural thing you would think of. So we'll have the prover send really long messages that the verifier will not read fully, but instead it just will query a few symbols of the prover's messages to make its to determine its new instance. Okay, and so actually it turns out that this is not sufficient, or it's not expressive enough of a definition to give us what we want. And intuitively, this is because sort of the verifier needs to sort of resolve all of these intermediate oracles that's receiving to the prover and then output a short instance on its own. Whereas in reality, we would like to have these relations be able to reason about the long messages themselves. Okay, so this sort of motivates the actual definition of an interactive oracle reduction that we'll be working with. Okay, so the idea now is we're going to consider sort of a ternary relation where there's both a short instance x as well as a long instance y, okay, in addition to the witness. And in order for the verifier to be succinct, similar to the prover's messages, we're not going to allow the verifier to fully read in the long instance y. Instead, it's going to have query access to it. Okay, so again, the prover's messages are long. The verifier will now make queries to both the prover's messages as well as the long instance. And then it will use this information to decide the new instance, as well as a new long instance. Okay. And now the new membership claim is if the new short instance, new long instance, and new witness are in the relation. Okay. So obviously a verifier, if it needs to be efficient, cannot fully output this long instance string y prime, right? And so what we're going to do instead is allow it to output sort of a virtual oracle, where this virtual oracle is sort of defined with respect to all of the oracles that it's seen so far. So the old instance oracle as well as any proof oracles that the prover sent during the interaction. Okay. So formally we can say that this verifier outputs some algorithm A, and A sort of can determine what y primes is on the fly. So you ask A, okay, compute me the ith entry of y prime, and now A is going to take I and then look at the other oracles and use this to determine what y prime of, what the ith entry of y prime should be. Okay, and importantly, we would require this to have small locality. So in order to determine the ith entry of y prime, we're going to need this algorithm to only inspect a few entries of y in the proof oracles that's seen so far. And it should become clear why we need this in a moment. Great. So let me also define what completeness and soundness should look like for IORs. So again, completeness is fairly straightforward. If x, y, and w are in the old relation, then the new x, y, and w will be in the new relation. And for soundness, we're actually going to need something a little bit more subtle. We're going to base soundness on proximity. Okay, so let me define this language Lx, for any short instance x. It's basically going to be the set of the long instances y, which correspond with x in the language. Okay. And so the soundness guarantee for an IOR is basically, if this long instance that you provided the verifier is sufficiently far from this language, okay? By far, I mean in terms of Hamming distance. Then with high probability, the new instance will be far from the new language induced by the new short instance x prime. Okay. In general, we can also expand this to work with promise relations in general. For this talk, I'm just going to focus on proximity. Great. So now I'm going to just give a few examples of what actual IORs look like. We've actually seen all of these today, so I'm just going to run through them pretty quickly. So the first is this sort of folding IOR that we saw in Ali's talk. And basically, here's the setup. We have some code C. Let's assume it's a linear code. And we want to test proximity to the interleaved code. Okay, so recall that an interleaved code, I'll call it C squared, is just the set of 2x(n) matrices such that each row of this matrix is a code word in C. And we're going to measure proximity based on column-wise distance. Okay. And so here the IOR is fairly straightforward. It's a single round of interaction. The verifier is just going to sample a random element, send it to the prover. And this actually immediately defines the new instance oracle that we're working with. So it's just the random combination of the two rows from the instance oracle. Great. So we started off with some claim, is y close to the interleaved code? And we reduced it to this claim, is this virtual oracle y prime close to the base code? Okay, and let me note here that this virtual oracle has locality 2. Right? So if you want to query any individual entry of y prime, it actually suffices for you to only query the corresponding column of y, and then take the random combination yourself. Okay. So let's see how we can use this IOR. So suppose you already had a proximity test for C, and now your goal is to build a proximity test for C squared. It turns out that using this sort of interleaved fold gadget, you can do this fairly easily. So let's say I want to test proximity of y. I first run the interleaved fold IOR to produce this virtual oracle, which is the fold of y. And then I just run the proximity test for C on this virtual oracle. And in particular, whenever I would query some entry of this virtual oracle, I'll sort of forward this to queries for the original oracle y, and then calculate what the result should be itself. And so here's why locality is sort of important. It basically enables for query efficient composition of IORs. Okay, so here's another example of an IOR. I will refer to this as the code switch gadget. So let's say you have two codes C and C prime, and you want to test proximity to C. Okay. So what we're going to do in this gadget is have the prover send the decoding of Y, except re-encoded under the new code C prime. Okay. So the claim here is that pi, the proof that the prover sent, decodes to the same thing that Y decodes to. And now the verifier is just going to take a sample random index, compute, query the value at Y, and then define the new oracle to be the proof oracle that the prover sent. And then the new claim actually is that Y prime is close to close to the new code C prime, and more precisely a subset, like a constrained subset of this code. So really what I like to think of what this code switch gadget is doing is basically taking a proximity claim for some code C and then moving it to a proximity claim for some other code C prime. Okay. And this already basically gives us a proximity test just by composing these two simple gadgets as we saw. If I Okay, great. Right, so just by composing these two gadgets, we can actually already obtain a fairly simple proximity test. So we can sort of have a sequence of progressively smaller codes, C1, C2, C3, and so on. And then we can sort of work with the interleaved code of C1. We sort of fold it to testing a proximity claim about the base code C1. And then we switch to the interleaving of C2. And then we just repeat this process over and over again. And at each iteration, sort of shrinking the size of our statement by a factor of k. Okay, so this was sort of the simple proximity test that we saw earlier today. Okay, so let's now talk about standalone reductions. So let's say I have this interactive oracle reduction. It turns out that similar to how you can compile an IOP to a succinct non-interactive argument, you can do the same thing for reductions. Essentially using Merkle trees and Fiat-Shamir, you can compile an interactive oracle reduction to a succinct non-interactive reduction. Okay, and let me be a bit more precise about what this transformation does. Basically, we're going to be working with, once we compile this reduction, we're going to be working with a new sort of set of relations where the instance now has the original short instance, as well as a commitment to the long instance. And now the witness contains the long instance as well as the witness. Okay, and I won't talk about it here, but we're also going to, it's necessary to work with some strengthening of soundness called knowledge soundness in order for this notion to make sense. Okay, so we have a recipe for converting an interactive oracle reduction to a succinct non-interactive reduction. What can we actually do with succinct non-interactive reductions? So for the rest of this talk, I'm going to focus on a specific kind of succinct non-interactive reduction, which I'll refer to as an accumulation or folding scheme. Okay, so the way I like to think about an accumulation scheme for a relation R is that it's simply a reduction from the product R times R star to R star itself. And R star here is some sort of arbitrary relation that you can define for the purpose of your proof system. Okay. So this is what it sort of looks like unwrapped. If I have a membership claim in R and a membership claim in R star, I can run this reduction in order to convert this into a single membership claim in R star. Right. And the goal of an accumulation scheme is sort of to be as lightweight as possible, especially compared to a succinct argument for R. So it turns out that if you have a succinct argument for R, you can always build a trivial accumulation scheme just by running the argument itself. But it turns out that sort of by leveraging the fact that we don't actually need to fully prove anything, we can make these proof systems much more lightweight for both the prover and the verifier. Okay, so if I give you an accumulation scheme, what can you do with it? So let me first give one example, which is sort of the most intuitive. It's what you would sort of think of, you would first think of given an accumulation scheme. So let's say the prover has a sequence of statements that it wants to prove to the verifier. And so if you had a succinct argument, then you could always just run the succinct argument prover on each one, provide the proof to the verifier, and the verifier could just simply check each one of them. Alternatively, if you had an accumulation scheme, then you could sort of run the accumulation prover at each step, give the reduction proof to the verifier, and the verifier can simply maintain a running sort of instance in the accumulator relation over the course of the entire interaction, right? And so at the very end, now it only needs to check one thing, amortized over the entire sequence of statements. This is sort of, this can be ignored. Okay, so really what I want to point out in these two pictures is that they actually look remarkably similar. In the top picture, we're sort of running this argument prover and the argument verifier. And in the bottom picture, we're running the accumulation prover and the accumulation verifier. So if we can construct accumulation schemes that, for example, have a faster prover or a smaller verifier, then we can make the overall proof system more efficient. Okay. So I want to give one more application of an accumulation scheme. And that's to build these proof systems called incrementally verifiable computation. So here's the setup. You have some sort of computation that you can represent as basically sequentially applying some step function f on some state. So you could think, for example, like a virtual machine or blockchain, something like this. And what an IVC proof system allows you to do is basically generate these proofs incrementally. So there will be an IVC prover who, given the state, the initial state, will produce the next state as well as a proof certifying this intermediate state. And you can repeat this over and over again. And at any point in time, you can run the IVC verifier on the current state as well as the current proof to decide the validity of the entire computation. Okay, and crucially in IVC, the work of the prover as well as the work of the verifier should be independent of the total number of steps in the computation. Okay, and there are also generalizations of this to other types of computations. This is more generally called proof-carrying data. Okay, so if you look at how IVC proof systems are constructed, the sort of classical approach is to take a succinct argument and intuitively run the argument prover on some circuit which computes both the step function f as well as the argument verifier, which checks that the previous proof was correct. So at every given step, you're going to prove not only was this step of the computation correct, but also the previous proof would have been accepted by the verifier. Okay, and it turns out that using an accumulation scheme, you can sort of build an IVC proof system that again looks very similar to the IVC from succinct arguments, except instead of running the argument prover, you're going to be running the accumulation prover. And instead of proving a statement about a circuit that contains the argument verifier, you're going to be proving a circuit which contains the accumulation verifier. And so again, if we can construct accumulation schemes where the prover is more efficient than a corresponding argument prover, and the accumulation verifier, when you represent it as a circuit, is smaller than a corresponding argument verifier, then you can obtain an overall more efficient proof system. Okay. Sorry? Yes, yes. Right, yes. Okay, so good. So before I want to talk about how IORs can be used to build accumulation schemes, I want to sort of give an abstract view of what prior accumulation schemes, such as Halo or Nova, do. Okay, because this will sort of inform how we construct hash-based accumulation schemes. So my claim is that a lot of these accumulation schemes have some sort of information theoretic core protocol that don't work with any specific cryptography at all. So previously, you would use like some sort of homomorphic vector commitment based on the security of group-based cryptography. But first, let me try to isolate this information theoretic protocol. So roughly the idea is that the verifier has access to these two inputs, x1 and x2, and it wants to test whether two vectors, v1 and v2, are in some languages, and these languages will be induced by the x1 and x2 values. Okay. So what all of these prior accumulation schemes do is that they'll basically run this verifier, except this verifier will not have access to v1 and v2 themselves. So it'll be sort of oblivious to what the actual vectors are. And instead, using the help of the prover, it's going to output some new x, as well as some random scalar r. And the new claim will be that this combination of v1 and v2 with respect to r is in some new language induced by the new short instance x. Okay. So let's say you have such an information theoretic core. If you want to convert this into a proper accumulation scheme, you can just apply a linearly homomorphic commitment to v1 and v2. And this is what the accumulation scheme looks like. So the verifier will now, instead of receiving v1 and v2, receive a commitment to v1 and v2. And it can actually compute this random combination of the commitments itself. Right? So it'll output some new commitment, which is obtained by adding the first commitment and the second commitment. And because this commitment scheme is homomorphic, an opening to to this random combination of commitments is precisely the corresponding random combination of the input vectors v1 and v2. Okay. And so sort of the way that we got into building these hash-based accumulation schemes was to ask, can we use commitments that don't have any sort of homomorphic properties attached to them? For example, a Merkle tree. Okay. So the answer is yes, and I'll try to explain at a high level how we do it. Roughly speaking, the idea is that we're going to take this core protocol and lift it to an IOR, such that once we compile this IOR using Merkle trees and Fiat Shamir, we'll obtain a hash-based accumulation scheme. Okay. So how does this look? The intuition is that instead of working with v1 and v2 themselves, we're going to sort of robustify this procedure by encoding everything with some code C. Right? So previously I had some claim that v1 is in some language and v2 is in some language. I'll now ask, is some oracle y1 close to the set of code words corresponding to the encodings of this language? And is some oracle y2 close to some set of code words which encode the other language? Okay, and now the output claim will be, is some random combination of these two oracles y1 and y2 close to the set of code words encoding the output language? Okay, and now it's fairly straightforward. We just run the exact same core protocol, but now instead of outputting some commitment to the random combination, we're going to output the virtual oracle, y1 plus r times y2. Okay. So this is sort of at least one component of the IOR which will compile to a hash-based accumulation scheme. Okay, so take this protocol that I've described here, and I'm just going to compress it into this gadget, which I'll call a fancy fold. Okay. So what does fancy fold do? It takes two input oracles and it reduces individual proximity claims on both of them into a single proximity claim on the virtual oracle. And so if you sort of look at this by itself, it seems like we're already done. We've taken two claims, we've reduced it to one, but it turns out that we're not there yet. And that's because fancy fold outputs some virtual oracle, right? You'll recall that a virtual oracle is actually, this virtual oracle is defined over these two actual physical oracles. So if we were to actually compile this protocol directly to a hash-based accumulation scheme, you would have to carry around these 2 Merkle commitments as opposed to 1. And this sort of precludes the type of accumulation schemes that we want to construct. So what are we going to do instead? We're going to run a code switching protocol. And in particular, we're going to code switch to the same code C. Okay, so let me just finish what the diagram does. The code switching protocol takes this proximity claim for a virtual oracle to the code C and converts it to a proximity claim, again, to the same code, but this time with a real oracle. Okay, and I want to sort of take a moment to pause and note that the fact that this is the same code is kind of weird. So if I told you that I was going to run a code switch protocol and switch the same code in the context of an IOP, it would be extremely stupid. There would be no reason to do it, right? Because anytime you would want to query this oracle, you might as well have just queried the virtual oracle anyways. But the interesting thing is that when you want to build like an accumulation scheme, you really don't want to work within a virtual oracle. So in some sense, we're constructing this IOR, which outputs a physical or a real oracle. And this overall protocol is suitable for compiling to a hash-based accumulation scheme. Okay. One other note that I want to make is that if you compare this to the sort of simple proximity test I gave earlier, in the simple proximity test, you're sort of running this sequence of folds and code switches, right? Fold, hop, fold, hop, fold, hop, until you arrive to a statement that's sufficiently small. But here, when we're building this IOR for an accumulation scheme, we actually only need to do a single fold and a single hop. And sort of this is where we can expect to get a more efficient prover and a more efficient verifier. In fact, using some optimizations, you can actually have a verifier that performs strictly fewer queries than any of these hash-based IOPs, as well as a prover that makes. Okay, I don't want to claim anything too strong, but makes fewer field operations and hashing than a corresponding argument prover. Okay. So that's all I want to say about accumulation schemes. Let me sort of move to the summary. So sort of the main takeaway that I want to give is that IORs enable extremely modular constructions of IOPs. And we've actually seen this throughout today. In fact, if you look at how actual practitioners are sort of implementing these protocols and also formally verifying these protocols, they look a lot like basically taking these gadgets, IORs, and composing them in a very generic way to build bigger and more intricate protocols. So in particular, I want to highlight that, for example, ArcLib, which is this library aimed at formally verifying cryptographic proof systems, I think we'll see more of it tomorrow as well. They actually use a slight generalization of IORs, a functional IOR, as the main object in their formalization effort. Okay, so one more thing. Before we get too gung-ho about IORs, I sort of want to also sanity check one thing. So previously I gave this picture of a proof system for proving a claim A, and I said, okay, well typically we're going to reduce it to some statement B and reduce it to some statement C and so on. And the rough idea is that if you have the soundness error for these intermediate reductions be small enough, then the overall soundness error, which is bounded by the sum of these individual errors, will also be small, and we're happy. It turns out that, I think one reasonable question to ask is whether all IOPs should satisfy this structure. And the answer is no. So for example, if you consider an interactive oracle proof that has soundness error, like let's say 1/2, and I just repeat it sequentially a bunch of times, then I can amplify the soundness error intuitively. But there's actually no way to decompose it into these interactive oracle reductions, which each individually have low soundness error. But I want to make the claim that essentially every IOP that we're sort of interested in actually already obeys this structure. So in particular, if you want to build an IOP that compiles to a non-interactive argument, you're sort of always implicitly working with IORs. So specifically, when you prove an IOP is Fiat-Shamir secure, the standard way to do this is to prove this strengthening of soundness called round-by-round soundness. And actually, the way I like to think about round-by-round soundness is that it's equivalent to basically stating that your IOP does decompose into IORs, and in particular, one-round IORs. And so from this standpoint, sort of IORs are complete in some sense. Yeah. Yeah. Yeah, okay, so if you had this virtual oracle that actually depended on two other oracles, then you would need to keep these two other oracles around. And if you imagine repeating this process over and over again, you would need to keep more and more oracles around, which is, yeah. Ollie? Yes. So I think it does decompose. It's just that in all of the rounds, the IOR needs to reason about the full set of oracles that's been sent so far. So as opposed to like these other IOPs where you can sort of forget about other oracles as soon as you switched, Fry is a special example where yeah. The state function encodes the languages that the IOR is reduced between. It's just that the languages are they just grow larger. There's more oracles to track. Yeah. So this is just something I want to put out there as like a way to think about how IORs fit into constructing IOPs. Okay. So the main takeaway for IORs for accumulation is that if you can build a suitable IOR, and in particular this sort of 2-to-1 IOR that outputs a physical oracle, then this immediately yields a hash-based accumulation scheme. And in fact, I sort of tried to give a generic approach, which is to take any sort of accumulation scheme which works with homomorphic commitments, lift it to some information theoretic core, and then show that actually we can turn this information theoretic core into an IOR and hence a hash-based accumulation scheme. Okay, and that's all I have. Thanks. Yep.
I was a bit hazy on how the code switching switches from a virtual to a real algorithm. Concretely, why does the code switching do that?
Yeah, so I think it'd be good to, yeah, like let's revisit the code switching gadget slide. So the idea here is that when we're code switching to the same gadget, actually, in the honest case, pi should be exactly equal to y. So it sort of seems trivial, but the point is that in the broader protocol, y is actually a virtual oracle. So the prover is recommitting to the random combination.
Oh.
Yes, and this becomes the new output oracle.
This is just a spot check? Like the new IR would just be a spot check IR, or is something more?
Yeah. So this code switching gadget, I'm also including the spot check. Yeah. Yes.
What is the formal definition of a virtual oracle? Is it an arithmetic circuit with like states, or is it like a Turing machine?
Yeah, I guess. Let me get to this. Yeah, I don't think you have to be too.
Like you can do things in the Turing machine that you can't do with just like it needs to be an arithmetic circuit.
Sure, but you can definitely do a Turing machine and then you just get more efficiency.
Okay.
So.
But it's not allowed to interact with the prover, right?
No. So just imagine that like whatever model you're in for the verifier, just imagine that like there's some corresponding algorithm in the same model, which just like the verifier has Oracle access to the things, but its only job is to sort of compute the.
But it can't, like, I don't know, bit decompose. I guess.
Yeah, so I also want to say like this sort of definition is still up in the air. So I did talk to Kwang, and they still have not finalized the definition of in a functional IOR. I think there's like a lot of intricacies here, but yep. What do you mean by packing?
Like Bing style packing, where I pack like many small field elements into a larger field element, and I have an oracle that only allows me to access polynomials over the large extension.
Yeah, I don't see why not. Your alphabet will just be different.
But that's an interactive protocol when I need to open. Like the prover needs to send me something.
Model the packing via, or you think actually whether the virtual oracle itself captures it?
Exactly.
Oh, no, I thought you meant that interactive reduction.
No, the virtual oracle itself. Like I have a protocol that's like operating over GF2, and it needs to like evaluate, but that evaluation in turns is actually a software protocol.
I think you could just model it as, like it's an interactive thing, just make your IOR bigger with that interaction and then make your A account for that. Not interact.
Like the composition of IORs, no?
Yeah, I think it's just a claim reduction, so you don't even need Oracle for it.
Sorry?
You don't even need Oracle for it. I think it's just a claim reduction. You just have a sort of
But like if I have
you construct a virtual Oracle.
If I have a protocol over GF2, it doesn't know if it's interacting with a, like it could feasibly not know whether it's interacting with an oracle that happens to be native over GF2, or it's a sub-protocol that you can go to get those evaluations.
Like all of the definitions here just in here.
Yeah, but
Like,
the virtual oracle got it,
but then it
takes any function of the index that is being queried at the oracle is access to and can do whatever it can do.
Yeah, okay, yeah.
That was my understanding.
Okay.
Any other questions for Solo? Okay. All right, so then I propose, so let's all thank the speakers today. Yep, thanks so much. It was, I think, a really great day of talks. So I propose that we go straight into the open problems. I hope that is all right with folks. Ron is going to disagree with me.
Should we do like a 2-minute break? People on bathroom breaks or something?
Yeah. Well, we can maybe.
Like a 2-minute break and quickly reconvene.
Yep, sounds good.
5 minutes. Sure.
All right. Drive a hard bargain.
Okay. There, I'm sort of starting from the end, and then I'm sort of
yeah.
There's like polynomials.
Do you want to connect the iPad in the
One's
right
five,
hand?
Yeah, I was thinking to go on hold. Yeah, that, but I guess I'm low on time.
And there's no charger.
But then I need to like pair my polynomial my GPR relation.
Yeah.
I'll just put a random IOPS slide on the back.
You don't want to connect your... What do you need for it?
I need a... Well, so I have to have a battery, so...
Connect it to my laptop to charge it.
Yeah, we can do that.
Wait, I have a thingy that connects to HDMI and power.
Yeah.
Maybe I don't have...
But I don't have a... I think there's no cable here unless we steal the one attached to this big screen. Like just a power cable. Sure.
Makes iPads happy, but only one way to find out.
Yep. Okay, cool. And then we can plug this in here. Yeah, I'm just concerned about running out of power in the middle. Okay. But we need, yeah. You have like a fancy.
Okay, do you want to drink one though? What version is laptop using?
Oh, we can. Yeah, I guess we can disconnect this light.
No, wait. Is there no power source?
I mean, there's this thing.
What were the laptops you were using? Nothing?
No, okay, we want that. I go to there. Power there.
Yeah, but I mean, this is not going to be super important.
Exactly.
But do we have a power source for this?
I actually, okay.
You need a charger. Yes.
Now it needs to be a miracle. Pray, pray. Apple was nice. Apple was nice.
Apple was nice.
That guy, good job. Great.
What's
That guy
good?
that Apple doesn't, good job.
Yeah, excellent.
Perfect.
All right, we're good. All
Now
right.
we need to spin mirror somehow.
Yes. So that should hopefully. Let me just open a new thing. Landscape.
You got experience from Simon as well, so about open problems.
Why don't we see it there?
I guess maybe they need to do something.
Or maybe you need to authorize the nasty.
No, I think the guys at the back need to put it on.
Yeah, I think they need to set it up.
It does show you mirroring somewhere, right?
Yeah, it's up here. So this I think is fine.
Are you ready for the open problems?
Yes, but if
Are
I
you?
had to do a talk now, I would just be like, okay, what next year?
I need to write one now. So this is that. Okay. Perfect. Beautiful. Cool. So we got open problem. We got. William has been formalized.
Oh yes.
You are formalized.